Okay, good morning. I'd like to welcome everyone. I'm going to introduce myself and then introduce my colleague, Pablo. Okay, thank you all for coming. Great to see you here. I think we'll probably have some more people coming in gradually over time. I'm Seth from Blockstream, and I'm going to be presenting about simplicity in the afternoon. And in the morning, my colleague Pablo is going to be presenting about Liquid. So we'll have a morning session on Liquid, then we'll have a break for lunch at 11:30. And then in the afternoon, I have a number of sessions prepared for you about simplicity and simplicity development. The final one involving some interactive examples for you to try on your own device. And then, of course, tomorrow we have the hackathon, and so I'll be talking about that in my presentation. Pablo, I realize that we may need to hook up another device for your presentation. He's able to present from there. Okay.
We'll see. Solid.
Yeah, if you want to switch to Pablo's presentation,
Let's see if it works. Is this working? Can you hear me? Yeah.
Okay.
Yes.
Sorry, we're just switching presentation devices. Do you need to grab that? Okay. There's an interesting degradation of the video when it's unplugged. It gradually fades away.
We suffered that many times yesterday.
I see. Okay, Pablo, when your presentation comes up, I'll turn it over to you.
Okay, let's get started.
Actually, I'm going to take my laptop away from here as well.
You have a clicker? I know Telegram is not ideal, but it's a good place to start usually. So we have those groups, the Liquid Development and the Liquid Community. I think Seth has another link for simplicity-specific stuff, but yeah, that's a good place to start always. Okay, let's get started. Hey everybody, good morning officially. I'm Pablo. I'm from Argentina. I'm director of engineering at Blockstream, and my day-to-day is basically anything that happens at the core layer of Liquid, right? Communication with the functionaries, updates, preparations for, and trying to make sure that for the user perspective, Liquid is as boring as possible. Right, so that nothing changes and everything just works all the time. It's not always there, but that's what we try. So, who has used Liquid, and who has used Liquid before Simplicity? I think that's okay. Nice. That's a good number. Are you aware of the features of Liquid? How did you? I'm trying to gauge how to present this, depending on where people are coming from. How did you hear about Liquid? How did you start? Let's start with you, if you want. Oh, you were. I know I see your face. Okay. Anything? Anybody? Same thing. Enviar issue. Okay. Yeah. Yeah, October 24, I think. Yeah. That was literally the first bootcamp. It's a miracle that bootcamp even happened, but it was really good. So let's start a bit with Blockstream. We'll get to Liquid in a bit. Blockstream, we are the technical providers for the Liquid Federation, and but we do a lot of different things, all related to Bitcoin. Many of you who have used a Bitcoin transaction in the past have used our block explorer, blockstream.info. We've been hosting it for years. The hardware wallet, the Blockstream Shade. We have our own service for Lightning or Greenlight. That is, it has cool features like it allows you to run a Lightning node and still keep the keys away from it, right? So you can have your keys in another location and still have the node running all the time. Obviously, about Liquid, we have another set of custody products for corporate, for enterprise that is coming later this year, and AMP, which is mostly related to the financial services that is built on top of Liquid. So the idea for Liquid came. Was published in 2014. Adam Back, Andrew Polstra, and others. This is a white paper. It didn't start as Liquid itself. It started with the idea of sidechains. And not only the idea for sidechains, peg sidechains, to make sure that everything that, all the Bitcoin that is circulating inside the peg network is actually guaranteed outside, right? One-to-one. That peg should never break, and the idea is to be able to validate it all the time and constantly in real time, so that people cannot basically rug pull from the sidechain. Let's start a bit with the similarities with Bitcoin and Elements. Elements, we like to say that is Bitcoin on steroids, really. Because the code base for Elements is roughly 80% or more of the code base for Bitcoin Core. In fact, if you wanted to synchronize the Bitcoin blockchain using Elements, it works right up to the activation of Taproot in 2021. The only reason why it stops working after that is because Taproot was designed and implemented first in Liquid, even though it was not activated. It was implemented first in Liquid. So the implementation varies a bit. So when the official Bitcoin activation happened in the main chain, the blocks are getting rejected. But up to that point in time, you can literally sit and do a full IBD of the Elements chain, of the Bitcoin chain using Elements. But how do we maintain that similarity? Basically, many years ago, we literally forked the Bitcoin code base, and we implemented a lot of features that we are going to speak about later on top of that base, on top of that version. Then, every day, all the PRs that are merged into Bitcoin Core are merged on top of that version of Elements. Every day is kind of an optimistic way. It happens. We dedicate some time to it. We stopped doing it for a while, and now we are back to it. We haven't released a version yet, but soon we are planning on releasing a version of Elements based on Bitcoin 29. It basically took us over 2 years to catch up to Bitcoin, because the last release version of Elements is 23. Right, so now we are catching up to 29. We are gonna release a release candidate of that, hopefully by the end of next month. So basically, it all goes back to Elements, which is the program that runs the Liquid chain and the Liquid testnet and other testnet that you want to do. Shares over 80% of the code with Bitcoin Core. It serves as a sandbox for new Bitcoin technologies. As I mentioned, Taproot was designed and implemented first in Liquid, in Elements, actually. It was activated on Liquid after Bitcoin, but all the initial designs and considerations were implemented on Elements first. Same thing with other features in Bitcoin. Schnorr signatures, again, for Taproot, were designed first in Elements. CSV, SegWit For instance, Segwit was also activated first in Liquid, and then it was ported as a software to Bitcoin. So we try to separate very clearly what is Elements and what is Liquid, right? Elements is the software that runs the chain. Liquid is just one instance of a chain that is run using that software. A good analogy would be in Bitcoin. If you run Bitcoin mainnet or Bitcoin testnet, you use the same binaries. You just tell which chain you want to run. And if you want to run a REST test network, you just configure a couple of parameters, and you can use a different network. Elements has basically the same concept. You could create a lot of chains. The most common one is Liquid. It's the default one, but that doesn't mean that it's the only one, right? Liquid testnet, which we are going to synchronize later, also works with the same binaries. And if you're testing something locally and you're creating an Elements REST test network, you use it with the same binary. Liquid is the first implementation of Elements. There are other private chains happening, but yeah, it is the most common. Sorry, I'm having a bit of an allergy thing, so I'm running out of breath, but hopefully we'll be fine. So as I was saying, if you wanted to do some testing, you can create your own blockchain with Elements. If you want to dig into that, the Elements tutorial shows you how to create a network exactly the same way as you do for Liquid, basically with signed blocks and all the features. There's another talk that is not part of the schedule for today, but that I usually give in bootcamps, and it's literally how to create your own Liquid network using the same software that is using the functionaries. Obviously, it doesn't have an HSM, so it can't be a production network, but it's good enough to show people how the programs interact and how the communication happens in real life. The idea is that you can run multiple networks, and for instance, this is just a demo, but imagine that you have the current Liquid network as it is today, and you could have sub-networks created by different entities that they could be either isolated for private trading, or they could be pegged into Liquid. And they don't need to be pegged at the LBTC level. Let's say that you create a network that is pegged to Liquid using USDT. So all the USDT that is circulating on Liquid is the native asset on a separate chain that you create for whatever reason. So there's a lot of potential things that could happen with Elements, right? Those subchains are not called Liquid. They are just other chains that could be created using the same technology that runs Liquid. So all the layer 2s have different trade-offs, right? It doesn't matter which chain. It doesn't matter if what you're doing. If you are creating a layer 2, it's because you need to optimize for something. But if you want to optimize for something, you are basically leaving something behind, right? So I usually discuss a lot with people with regard to why they don't like Liquid or why they don't like whatever other implementation. If you're doing a layer 2 to optimize for something and you are okay with the trade-offs, it's fine, right? It doesn't need to be as perfect as Bitcoin, right? If you're not okay with the trade-offs, stay in Bitcoin and it's fine. What I don't like is people lying about what the trade-offs are. We are extremely clear. We try to be extremely clear what are the trade-offs when you're using Liquid or any other elements-based chain, right? If you understand what are the situations, and you're okay with that, then you can use whatever you want. I don't like when some people attack Liquid saying whatever. Yeah, we know. We are not denying that. We are just saying that for some people, maybe for financial situations, it doesn't matter, the difference. So the security of Bitcoin, Bitcoin on a cold wallet, it can be improved, right? It could be annoying, but it is the best that you can do, right? Permissionless, again with Bitcoin mining, anybody can start mining, anybody can provide hash rate, and you can keep the network, can help keep the network running. But when it comes to confidentiality, Liquid has confidential transactions natively, which means that if I transfer something to someone, people are going to see the transaction from the outside world, but nobody's going to know what I transferred and for how much. So that type of transaction is much more private than whatever you have in Bitcoin, right? And if you want to optimize for speed, there's no better than Lightning. So we use sometimes Liquid as a complement to Lightning with swaps, because even though Lightning is extremely fast, for people that don't use Lightning that much, the whole idea of keeping your channels open and having to, and maybe not wanting to use a custodial wallet, or using a custodial wallet and suddenly you have your channels closed because you haven't used it in, I don't know, in a couple of weeks, or depending on the fee rate for opening and closing channels, it becomes annoying. So you gain a little more ease of use by using swaps on Liquid. You lose a bit with regard to speed, right? But you still can balance things depending on what you want to optimize. Continuing with Liquid features, I already mentioned a bit with regard to confidential transactions, but let's start with multi-asset. Liquid is natively multi-asset, which means that different to Bitcoin, Bitcoin is single asset. It's Bitcoin. That's the only thing that's transacted on the chain. If you want to do something else, you need to do something that is not generic in the chain. You need to create, I don't know, what people are doing with taproot assets, which I don't like, but that's my personal opinion, whatever. I don't think it should live on the main chain, but I'll leave it at that. Anything on Bitcoin is Bitcoin. When you move to an elements-based chain, and Liquid in particular, the chain supports multi-assets natively, which means that you can issue your own asset that is traded natively on the chain without any smart contract. Okay, for instance, you want to create your own token to play with your friends, or to say, I don't know, to make a raffle for the end of the year, whatever. You go into the Elements RPC, you create your own asset, and that's it. And you can send it to someone, and there's no restriction, there's no need for knowledge with regard to smart contract. It's just one more asset, okay? And that makes a lot of the movements on the chain a lot simpler, because you don't have a risk associated with an asset that is present in EVM chains, right? You don't need to know how to write a smart contract, how to make it secure, how to teach a specific protocol or a specific hardware wallet how to treat it. It's just native to the chain. So if you send asset A or asset B or LBTC, which is the Liquid representation of the Bitcoin, it just doesn't matter. It's part of the chain. The other part that is native to Liquid two elements, and Liquid in particular, is confidential transactions. And I talked a bit about this before. So in Bitcoin, if you are sending something to another address, first, nobody knows who you are, but everybody knows what's being transferred. The asset is visible and the amount is visible. So anybody can see that a transaction of 1,000 Bitcoin happened. What it means, no idea, right? But anybody can see what is happening. In Liquid, all the transactions are confidential by default, which means if let's imagine the same transaction, one input, two outputs, right? The one goes to the destination, the other goes back to the owner. Nobody knows what type of asset that is because the asset is confidential. If I paid $5 for my coffee, or if I sent 1,000 Bitcoin, from the outside, the transaction looks the same. The other thing is the amount is confidential. So nobody can see exactly, not only what type of asset was transferred, also the amount is confidential. So nobody can see exactly what happened. And even if you don't want, if you don't care about the world seeing it, imagine that I need to make an LBTC payment, right? And I have my UTXOs consolidated in Bitcoin. Suddenly, the person that is receiving the transaction can see how much Bitcoin I have if I have it consolidated, because they are going to see the change address. They know what's theirs, so they can see how much is mine. In Liquid, the confidential transaction, it applies to each UTXO. So if I send someone 1 Bitcoin, doesn't matter, they are not allowed to see the other output in the same transaction, which is how much came back to me from change. So those type of things are extremely helpful with regard to privacy, and that's native in the chain. No, there is no extra service, there is no outside service. The chain itself handles that. There's a mention in there about AMP assets. We're going to speak about that a bit more, but it's more related to a special treatment of assets on a layer on top of the chain, which is mostly used for financial instruments. So let's talk a bit about how Liquid works. There are two. Let's divide this in three. First is the pegging, how to get Bitcoin into Liquid, the LBTC, the peg. Then is how to get out of LBTC back into Bitcoin, and then is the assets that are issued internally in the chain. The assets that are issued internally in the chain, they are completely outside of the scope of what we are doing here, because that is not related to the limits of Bitcoin. That is just something it's just a service, right? So it's completely unrelated to the peg-in, peg-out process. It's something that lives only inside Liquid, and that is basically a social contract between the issuer and the holder. Right? It has, at the chain, at the core level, it's just something that someone created. It's just hash, right? It doesn't have any special meaning. The only asset for the chain that has a special meaning is the LBTC, because it's the asset that needs to be held and pegged to the external chain. So, how do you do a pegging? Basically, you have an Elements wallet, any type. You get a pegging address that is a special Bitcoin address that can be used to, that then people send the money to it. They wait 102 blocks, which is a really long time, and it's kind of scary, waiting 16 to 17 hours before you can claim your Bitcoin. but it's for security reasons what it needs to be. The reason why we chose 100 blocks is because it has a special meaning in Bitcoin. In Bitcoin, the miners need to wait 100 blocks before they can use a reward. So because the Bitcoin assumes that there will never be a reorg larger than 100 blocks. So if the miners need to wait 100 blocks to spend their money, we need to wait 100 blocks in order before you can claim your pegging. That's basically the logic. It's the same as Bitcoin, right? Yeah.
What is the two more blocks coming? Where is the two more blocks coming from?
Just to avoid inconsistencies when you try to claim it, because elements, let's say that your block is a little behind, and literally, if you do it at 100 blocks, it works. But if you try to claim it from within elements, it's going to make you wait 102 blocks to avoid problems broadcasting that transaction if another one of the nodes that you're broadcasting through, they don't have the latest Bitcoin blocks. So basically, it's just a padding that the Elements client does to avoid problems broadcasting the transaction. From the chain's perspective, it's 100 blocks. But from the wallet's perspective, to avoid problems with that broadcast, let's wait a bit more. That's the meaning of the extra 2. If you claim at 100 and you manage to get it working, it works. So, and when you claim your Bitcoin, your LBTC inside Liquid, you get the same amount. It's 1-to-1, right? You pay for the transaction fee, but that's it. And that is true for now. It's going to change a bit soon. We're going to talk about ellipse, and I'm going to explain that a bit later. But that's basically how it works. That UTXO that you send goes into a special wallet where all the UTXOs from the peggings are kept. So basically, you can guarantee that whatever's circulating inside of Liquid has the corresponding BTC on the outside wallet. And that is something that anybody can validate. In fact, Mempool, which is another block explorer, they have a graph constantly auditing Liquid along for the entire history, right? And they basically showed if at any point in time there was an event of a depeg, which means more money circulating inside Liquid than that it is being held in the wallet. And obviously that number is 0, and it should always be 0. But a couple of years ago, they had a bug, and it was showing 1, and it drove me crazy, and I harassed them until they fixed it. Yes?
You said before that peggings are testless, but you have to send the BTC to special address.
Yes.
So I kind of think behind that special address there is a central authority or something like that, a federation.
You are literally sending your BTC to the federation, and you have to wait those 17 hours until you can claim it. You can do it yourself. There's one thing that's important. The federation has no idea about your pegging until you claim it. Even though technically the federation has the keys to spend it, there is a special value that only you hold until you can, that is used to do the claim. So even if I'm scanning the blockchain, I cannot see that you made a transaction that is going to be later used as a pegging. Until you claim it on the Liquid side, you reveal that information, and then that information can be added to the wallet. Until you claim it, nobody can see it. Sorry, no, it's not. Okay. That is how you peg in to Bitcoin, into Liquid. Now, how you peg out back to Bitcoin. This is where it gets a bit annoying, and it's all about security. There is a process called pegout, which basically means that you burn your LBTC inside of Liquid, and you get your Bitcoin back into the Bitcoin chain, into a specific address. The problem is that that process is only reserved for Liquid Federation members. And the reason is simply a matter of security. And for us being way too paranoid. Let's say that someone finds a bug in Liquid, so bad, so heinous, that they are able to peg out all the money, right? If the process were completely open, the money is gone, right? And there is no way to recover from that. But imagine the same situation in the same bug, but only Federation members are allowed to do that. And not only they are allowed to do that by themselves, they need to do it into a wallet that is a cold wallet where a well-known descriptor, which means that we don't, let's say the same case, something happens, we don't know which one of the wallets received it, but we have a list of 50 people, 50 companies that may have received those coins. It adds a bit of friction to the process, but it makes the network much more secure. So nowadays, with all the swaps services available, the fact that not everybody can do a native pegout is not a real problem, right? If people normally uses bolts like swaps like bolts or even side swap, and they get their coins immediately. So this process is mostly reserved for companies that are going to do pegouts of significant amounts, right? Last week there was a pegout of 40 Bitcoin. Right? I don't think anybody here has 40 Bitcoin, otherwise they'll not be here. So, so the idea is the native pegout process is reserved for companies, and normal people, when they need to peg out, they just use a swap. And this restriction actually becomes meaningless. Yes?
Two questions. When you're doing a peg out, there is not a single wallet that is receiving all the money that are going to be pegged in. There is a distribution of the wallet that are receiving the money, right? Each federation is holding a wallet that might receive the pegging.
Exactly. Each federation member, they have their own authorized wallet from the Liquid side and their own hardware wallet where they might receive their own coins. What I'm saying is, if there were this horrible bug that we know it doesn't exist, but it doesn't matter, someone would peg out, it would be in one of those 50 wallets, right?
Since there is a limitation on the Liquid, as I know. But when you're burning assets, it means you're sending them to unspendable address, and you receive your Bitcoin back. So how does this ratio work? When you burn assets, you reissue assets if anyone else again comes back to the Liquid, or
Exactly. Basically, I can show you a transaction in the Block Explorer after. But the idea is, when you do a peg-in, you have basically the input of the transaction is marked as an input from an external chain. So basically you're saying, hey, this input from Bitcoin, we simulate it as an input from Liquid, right? And then we do the transfer. When you do a peg out, say, okay, that thing that came, I'm gonna burn it and I'm gonna transfer it. But so basically the circulating amount is gonna go down. Then the next time someone does a pegging, you're gonna get something that looks like that's an input from the outside world. So you are literally just, it's like inflation, but it's internal inflation from coins that came from the outside. So you'll never have more liquid Bitcoin than the 21 million that can come out from the outside world.
Okay, so currently there is only, I don't know, let's say X amount of liquid Bitcoin.
Around 4,000, yeah.
4,000 on the liquid Bitcoin that are missing from Bitcoin. There is no like.
They are not missing.
No, they have been transferred to
correct.
specific addresses.
Correct.
Stay not in the circulation of the.
Yeah. So they are not missing, and I can show you the wallet, and they are there. They are just, yeah. They are not circulating in Bitcoin. They are there. Yes.
Is there like a burn function, or burning just means sending to an address where nobody has to keep?
You can literally do a burn inside Liquid and burn to nowhere, right? I don't recommend it, but it can be done. In fact, for different reasons, I have to do it all the time. Or you can do the special burn, which is from an RPC called send to main chain, where basically you say, hey, burn this, but give me the same amount on the outside. Okay. So it's both things end up with the same result, less LBTC circulating inside Liquid, but one is.
But if I burn natively, so without getting anything back, I'm gifting some real Bitcoin to the Federation.
Literally, exactly. And literally, that's you can do the same thing by transferring Bitcoin to the wallet, but not to the special address for a pegging. Literally, we call that a donation.
But you told me about these nodes, special value that my client have and that the Federation cannot access. Yeah. So is it a real gift? Can you use it after I burn? Or it's just an almost gift since neither you nor I can use that Bitcoin?
Okay. So think about it this way. You have the LBTC circulating inside, and you have the Bitcoin held in the outside wallet, outside being Bitcoin. Let's say that I need to, I haven't gotten into this yet, but the UTXOs in the wallet, in the outside wallet, they need to be swept constantly back into the same wallet. I'm going to explain a bit later. But let's just say that it needs to happen. If I have one BTC circulating inside Liquid and one BTC in the wallet outside, I cannot sweep it because if I spend in the fee, I break the peg, right? Because I'm going to have less coins in the wallet than what is circulating inside, and that can never happen. So the process that we do normally to make that work is make a donation, send to a specific address that cannot be used for claiming later. So basically you have more coins in the outside wallet than what's circulating inside. Or you burn LBTC on the inside. So suddenly you have less circulating than what's on the wallet. So that extra can be used to pay for the transactions.
So this cost is reflected to the end user, right? Or is absorbed by the foundation or something like that?
Normally, this cost is absorbed by the federation. I'm going to talk about the user pays for paying later, UPP, but normally that cost is subsidized by the fees that are received from every Liquid transaction. Okay. Basically, what we do every once in a while is get some coins out of the wallet that receives the fees from the Liquid transactions and burn to create that imbalance so that coins can be used on the outside. Okay. Any more questions? No? Okay. How does Liquid work today? Basically, Liquid has predictable 1-minute blocks, which means that every minute you have a block. There is no proof of work, as in Bitcoin, where we basically when's the next block in 10 minutes, and it's always the same answer. In Liquid, you know that every minute you're going to have a block. If one functionary is offline and there are problems with communication, you may have to skip a block, but it's not the normal situation, especially now that when we introduced what we call the backup master, which is even if every minute one of the functionaries proposes a block and the rest of the nodes sign it and add it to the chain. Up until a few years ago, if the one that was supposed to propose the block at that minute was offline for whatever reason, that round was skipped, right? Now, then we introduced a feature to say, hey, oh, is 4 offline? Don't worry, I got you. Here's the block, right? And so it's not very common nowadays for a round to be skipped. From the protocol perspective, you just skip a minute. It's not a big deal. But for predictability, it's much better if that doesn't happen. So I keep talking about 1 minute, 1 minute. That's a configuration thing. In Liquid is configured to have 1-minute blocks. In any other elements change, you could have 1 second, 5 seconds, 10 minutes. It really doesn't matter, right? For instance, in our CI environment, we have 3-second blocks for different chains because we want things to happen really fast. In real life, 1-minute block is what was decided when Liquid started. And today, even though technically we can change the round times, it's going to break a lot of assumptions that people did around Liquid, assuming that every block is 1 minute. So let's imagine that you do a CSV in Bitcoin to control how many blocks you want to wait. You're not thinking about blocks. You're thinking about what blocks means with regard to time. If you change the time, you're changing the assumption that people did. So that's why, even though technically we could change the block time, it's very unlikely that we will. Right. One thing is the 2-minute settlement, 2-block settlement. When I was talking about the reorgs in Bitcoin and the 102 blocks, we were saying how much time you need to wait to make sure that the transaction is final, right? That it cannot be replaced by another block. In Liquid, and this is a Liquid thing, not an Elements thing, that you can always generate the same block again, even though it has never happened, but you can never go back. Let's say that the chain generated block number 10. It can try to generate block number 10 again because the HSMs will allow it. It could happen because one of the functionaries was disconnected or something, so they can try to create another block again because there were not enough signatures, whatever. But they will never sign block number 9 again. So if you see your transactions and there's another block on top of that, that's it. So finality time from the real technical perspective in Bitcoin is around 17 hours. In Liquid is 2 minutes. How does it work? 11 out of 15 functionaries, which means that there are 15 functionaries distributed in different countries, in different places in the world, in different legal jurisdictions. Every minute everybody knows who's going to propose a block. Okay? They all have an internal ID, and everybody knows who's who. So one proposes a block, all the rest are going to validate the block, and they are going to provide their signature, saying, yep, that block's fine with me. If one is offline, it doesn't matter. As long as you don't have 5 offline, the network can just keep going. That's why the 11 out of 15. If someone proposes a block that literally the rest doesn't like, a malicious block, that's basically going to act the same way as if they weren't online. They're going to look at the block and they're going to say, I don't agree, I'm not signing that. And that block cannot be produced, which means you, in order for the network to produce something that is malicious, you have to have 11 malicious actors. Okay?
Why we wait blocks if from the endpoint point of view, the end user, we will never have a reorganized.
Yeah.
Right, there is not a possibility to reorganize since it's a federation.
Why wait too?
Yeah.
It's mostly it's mostly about the fact that it technically can happen.
Okay.
So imagine it. So let's say that you are online, you propose a block, but there's nobody else, right? So you propose it, and you don't get an answer. You already got your signature from your HSM, right? So your HSM already knows that it's signed block number 10. The rest has no idea. Suddenly, everybody connects again, and there's another one. They haven't seen your version of block 10, right? And it's not part of the chain because it only has your signature. So they propose block number 10, right? When they propose block number 10, you're going to tell your HSM, hey, sign block number 10 for me. If you block that from your HSM, it's very easy that if that happens 2 or 3 times, the network gets stalled, right? Because the HSM is not going to sign it. So you need to allow the HSM to re-sign the same height.
Because there is not the need for the confirmation response. A validator does not really listen the network. So because if I were alone or if I were disconnected and not available to the other peers, and I produced a block and I never got a response, my logic I would just simply assume that it automatically invalidates.
That invalidates your block, but the idea of not letting the chain go backwards is in the HSM.
Okay, so I can only recreate that same block, but okay, yeah.
So basically, in theory, there could be a situation, let's say that you have 15 nodes and one is one behind. Let's say in theory, we all agree we created block number 10. And suddenly it's a turn to create a block of the one that is one block behind. And they create block number 10 again. The others are going to say, what's this idiot doing? We already have 10, but whatever, we can do it. Let's sign it and move on. So in theory, you can have a case where you regenerate the same height, right? In almost 4 million blocks, it has never happened. But in theory, it can. So we don't use that as a reference. Once you have one block on top of that, you know you can't go back. That's why we use that 2-minute finality or actually 2-block finality.
Yeah, because if I were like 10 blocks behind, I would propose block 10 while you are on block 20, and you just discard the proposals. Exactly. This is not the block you're working on.
Exactly. But the same that we did last time is valid. Going back is not valid. So, in fact, one of the features that we enabled, like, I don't know, 2 or 3 months ago, is that the same case that you were describing. You are 10 blocks behind, you propose something, and instead of everybody else ignoring it, everybody else is going to say, what are you saying? And the backup master is going to say, don't worry, I got you. Here's a real block, right? So instead of missing that round, because the one that's supposed to propose something old, the backup master is also going to jump in as if the real master was offline background. Okay. So all of this generates the fact that every minute you have a block and you know exactly that when that block is gonna happen. Yeah, I guess moving the presentation from Google Drive to PPT moves a few things around. So let's talk about network roles for a bit. We describe a bit of how the functionaries work. Basically, they are the nodes that have the signatures in order to create a block in the network, right? So going back to the permission network versus permissionless, Liquid is completely permissionless to use, but not to participate in the block production, right? In Bitcoin, anybody can run a miner and participate in the block production. In Liquid, there's only a special list that can do that. Then you have the federation members, as I explained before. Anybody can peg in, but only a subset of the federation members have the ability to peg out. And then from the perspective, you can run your full node. I have it running in my laptop, right? I can do a pegging, and I can audit the chain constantly, but I cannot do pegouts. I could create my own transactions. I keep saying we, with regard to the chain, we, as in Blockstream, we are the technology providers. We don't own the chain, we don't run the chain, right? We provide the technology and the hardware so that the Liquid network can run, but we don't have any power over the decisions. Obviously, it's all part of conversations, but it's not that Blockstream runs the functions for the Liquid network. Yeah, different entities around the world, they run their own functions, and Blockstream provides the software and the guidance in order to run the network. Normally, when we want to propose something or make an improvement, we talk to the technology board of the Liquid Federation, and then with that comes a decision on how to activate things. The Liquid Federation has basically 3 boards. The membership board that decides who are the members that can into the federation and can participate in future decisions. Let's say that some company wants to join the Liquid network to have some sort of participation. The membership board is going to decide if they are allowed to do that or not. Then you have the technology board, which is the one that is usually the closest to Blockstream, that basically decides on what we propose, or they come to us and propose changes to the network. One of the changes that came from the technology board was the implementation that we call discount CT, which is a process that basically made confidential transactions in Liquid roughly 10 times cheaper than they used to be. Originally, something I didn't mention before, but when I talk about confidential transactions are roughly 10 times bigger than explicit transactions, which are not the default, but you can make explicit transactions in Liquid. So what happened was that because the transactions were bigger, people ended up paying more fees for using confidential transactions. And since we wanted to discourage people from using explicit transactions, we managed to get a different calculation in the way that transactions are weighted to analyze the fees. So nowadays, if you do an explicit transaction or you do a confidential transactions, even though it's 10 times bigger, the cost is exactly the same. Okay. And then you have the oversight board, which is the most boring one, which is comes up with the rules and everything for the other boards to adhere. This is kind of the same as I was showing before. You have the functionary operators, which are basically the core of the block production. The federation members that some of those are the ones that run the functionaries. Then you have the 3 boards, and then you have on the outside basically the full nodes that anybody can run. Yeah.
What incentivizes the full nodes to maintain a full node and secure the blockchain?
Basically, if you want to do a pegging, it's a lot easier if you have a full node. If you want to monitor the chain to make sure that everything is happening, the same thing you do in Bitcoin. Even if you're not doing anything special with your node, you run a node to make sure that everything is being validated and the way it should be. Okay, it's not and it helps others do IVD and relay transactions. Yeah.
So the goal of a full node in Liquid is not to choose, rather to just be alert if something goes on.
Yeah. Basically same thing you do running a full node and a full Bitcoin node in your house. You get nothing out of it other than being monitoring the situation.
Yeah, in the case of Bitcoin, maybe you have some voting power. Let's say.
Unless you're mining.
No, I mean on the implementation when we adopt the software, or I hope not a hard fork.
But again, you choose which side you stay. Let's say in the case of a fork in Bitcoin, you choose which side you stay depending on which binary you're running. But as long as you're running on that side, you're only validating that it's going that way. In Liquid, you basically get the same case, even though there is, unless someone duplicates the keys to sign the blocks somehow, there is not going to be a fork in that sense, right? In Liquid, there will be a fork soon. It's not a technical. It's more like a bug fix. There was a limitation, the 21 million limitation that obviously that Bitcoin has. There was a bug in Elements from the early days that was also limiting to 21 million for issued assets, which makes no sense because the limitation in Bitcoin has nothing to do with the assets that you can issue for yourself.
Another part on the Elements,
Yeah.
on protocols built on Elements. It's just, okay, we create a new federation, we migrate everything there, and we are up and running with the new software.
Basically, we are going to tell everybody, hey, update to this version, otherwise you're going to get left behind. There is no two chains. We are going to get to that point. Somebody's going to propose a block that all versions are not going to like. A new version is going to say, yep, this is fine. So if you had the old version, you're going to stay there. You update, you say, hey, you know that block that you thought was wrong? Check it again. Oh, it's right. Let's move on.
And will there be a part of this presentation on block structure of Liquid, the mempool of Liquid, or are they pretty similar to Bitcoin, so I can assume their work?
It all goes back. Transaction structure, even though technically it's the same, it has a lot more information because of the blinding. We try. That part is pretty technical detail. We try not to cover it in the presentation, but I can point you to a document that has literally the whole structure. With regard to mempool and relay and all the peer-to-peer, it's basically that part that we inherit from Bitcoin Core, we practically don't touch.
Okay.
So it's mostly the same infrastructure. You even have the same RPCs if you're used to using get raw mempool or get raw transaction or things like that. In Elements, they work exactly the same. yeah, a couple of faces of people whom you might recognize or not from who's who on the boards of Liquid. Yeah. You have, yeah, I think the most famous one, Samson, mostly everybody knows. Killian, who's the CEO of Bolts, if you've done a swap on Aqua or something like that, or even paid with the Blockstream app, you use Bolts, even if you didn't know. So, how things change or are done inside the Liquid network? We have the process that's called Ellipse. Basically, Ellipse is elements improvement proposal, the same as the Bitcoin BIPs, right? There is, obviously, that screenshot is from a couple of months ago. But if you look at Ellipse 201, that's basically since the fees in Bitcoin and Liquid are lower, there was a proposal by Killian from Bolts to reduce what's considered dust, because there were a lot of UTXOs that were considered dust that in Liquid they can be transferred and still be valid. And if you look at Ellipse 200, that's the one I was mentioning about reducing the cost of confidential transactions, right? 202, that's the one that I was mentioning about UPP, user price for pegging. The whole process, this goes back to the cost of actually running the Liquid network. I kept mentioning the 11 out of 15. The 11 out of 15 applies to both the block generation and the wallet handling. So what it means is that every coin that you send to pegging, it's held in a wallet inside in Bitcoin, like anybody would. The thing is, for security reasons, let's say that, again, paranoid stuff, let's say that the network goes down and it's completely unrecoverable, we don't want those almost 4,000 Bitcoin to be lost, right? Because if we lose the keys, or if someone attacks the network, they kill the keys, whatever, we don't want those 4,000 Bitcoin to be lost. So the actual script for the wallet is 11 out of 15 plus 2 out of 3, right? Those 2 out of 3 is what we call the emergency keys, right? The thing is, if those 2 out of 3 could be spent immediately, that would be a huge security risk, because anybody could get those keys and basically steal money from the Federation. So the 2 out of 3 can only be used after 4 weeks, after 4,032 blocks, which means while the Federation is working, those UTXOs are constantly being swept back to itself, so that the emergency keys can never be used, right? Then that has a really high cost, right? Because all the UTXOs are constantly being swept back to themselves. In a low fee environment like we have right now, it's not a big deal. Literally, it costs us 453 sats per UTXO. But in a high fee environment, there was 1 month, I think December 23 or something like that, where we paid over a Bitcoin in fees just for maintaining the network, which is unbearable, right? So here comes Ellipse 202. Yes. 4 megawatt units, same as Bitcoin. Yes, making sense. Sure. We have a proof of concept internally with Lightning channels inside it. They should just work. Making sense or not, in my opinion, it does, Make sense? Because you are able to detach the lining channels from the cost of opening and closing in Bitcoin. The fees in Liquid are much more stable. So if you want to open that, you can do it. In fact, we are working on a theory where you could intercommunicate channels that you have in Bitcoin with channels that you have in Liquid. So if you could, let's say, open a channel inside of Liquid and interconnect that to Bitcoin, and nobody knows that that you're routing through, it will make it a lot easier to keep channels open. On the block size. The block size we inherited from Bitcoin is still 4 megawatt units, but given that in Liquid, the block size is not related to the network security because the network security is completely related to the signatures, there's a chance that in the future, if needed, we can grow the block size without changing any of the security assumptions.
But
yeah.
these are not parameters that I can choose when I'm creating my own federated chain.
Yes and no. There's a soft limit and a hard limit. And since we inherit the hard limit from Bitcoin, it's still 4 megawatt units. And if we were to change that number, again, it would be a hard fork. Again, it's a technical hard fork because you're not going to say one chain or another. You're going to say, hey, update to this version before we move on.
I could maybe enforce some sort of smaller blocks without doing
You can. In fact, when Liquid started, the blocks were 1 megawatt units instead of 4 because of different optimizations. But since we were, that was a soft limitation on the configuration of the functions. So basically, we were able to bring it back to 4 without any problems. But 4 is the limit that we inherit in the source code from Bitcoin. So if we need to change that, we need to make a fork to allow it.
Why this was not made as parameters so that the specific chain could have a different block size, maybe to enable?
Mostly because we didn't think about it when we started. No, we haven't done this so far because we haven't needed to. But it's not it's more like, hey, do we want to do this now or do we do this later? That's it. So I was speaking about the cost of the peggings. The biggest cost for maintaining the network is what we call the first sweep, the first pegging, because the network doesn't control the size, the amount of that pegging, which means that in a high fee environment, suddenly someone pegs in 100,000 sats, and you can lose a big chunk of that pegging in the first sweep, right? After that, the network is going to try to consolidate. It's going to try to do a lot of things to optimize the cost. There's a project that we are working on in order to sweep to taproot instead of sweeping to SegWit, so that the subsequent sweeps are going to be cheaper. But the first one is from the pegging is the one that we can't control. So in order to try to discourage people from doing peggings that are going to be detrimental for the network, that's where UPP comes in, ELIP 202. Basically, the idea is the minute that you claim your pegging, if your pegging is below a certain threshold, that the network is going to deem, hey, you shouldn't be doing this, you are going to be paying a percentage of that in order to pay for the cost of a first sweep, right?
Only if it's a small enough.
Exactly.
Otherwise, you don't pay anything.
Exactly. Okay. So the idea for this is to discourage people from doing stupid peggings. Let's call it that.
But I see a pattern of cost not being reflected to the end user. And why is that? Is there a philosophy internal to Blockstream? Is there a reason?
Can you repeat that? Sorry.
I see a pattern of multiple choices that leads to a cost for someone that is not reflected to the end user, even if it's benefiting from the cost that you are sustaining.
Yeah.
So is there a reason? Is there a philosophy? I don't know, marketing, or it's just it's simpler like this, and we know that we can subsidize this cost in other ways.
So, in a high-fee environment, this can be considered an attack of the network, right? So, because you can say that you are forcing the network to incur in a cost to maintain what you give to the network, which you get in full. So, this is more a protection than anything else from the network perspective. If your peg-in is big enough, the network is willing to subsidize that, given the fees that are collected from all the rest of the transaction. If your peg-in is small enough, it's considered an attack, and it's mostly, let's call it spam protection. Yeah. Okay? It's also, let me clear something up. All the fees that are collected by the federation, they don't go to Blockstream, they go to the federation. No, but yeah.
But since I pay only a percentage of my packing, even if it's below the threshold, I could still attack, because there would be probably
No.
environment.
I said percentage, but that's not literally correct. There is a formula which is we wanted this to be deterministic, even if it's not perfect. So basically the way that this is done is the amount that you have to burn to claim that peg-in is related to the fee rate that you paid in Bitcoin when you created that transaction. So we are assuming, basically what we are doing is assuming a stable fee rate in Bitcoin. So let's say that you paid 100,000, 100 sats per byte. Okay, we are gonna assume that for us to sweep that transaction, it's gonna cost us 100 sats per byte, and that's what you need to burn. If you paid 1, it goes to that.
That's a big assumption. And it's
Oh, absolutely.
not always true. I mean, on average, it's true, because either you win, either you lose, and then on average, it's smooth out. But if I'm a particular sophisticated attacker with a lot of resources or medium size resources, I could, I don't know, study that when the markets in US opens, the fee starts going up because trader starts to use the chain, and so I just do some time-based attack where I peg in a deterministic environment in a moment where the fee are low, and I redeem when the fee.
Absolutely. So the idea behind this is, if you are thinking about doing that, yes, it's going to affect, but it's going to affect us much less than not doing it. Let's say that you try to do an attack like that. Unless there's a fee spike between 1 sat per byte and 100 sat per byte, it's still going to be better than not doing this. And also, one key point for us when we did this is we wanted to make it deterministic, right? So I know that assuming that the fee rate is going to be the same is a big assumption, but still, it's good enough to deter people from doing stupid things. Why deterministic? Because we wanted that transaction. Let's say that you create that transaction now, and you claim it in 5 hours, right? And you execute and you broadcast it in 5 hours. That transaction should still be valid. So when you create the claim, you should know exactly how much you're going to pay, because when you send the money to the pegging, to do the pegging, you know how much fee rate you paid. So you know exactly how much it's going to cost you to claim it.
We could say that you are optimizing for a user for usability of use instead of maximum protection of the federation.
Exactly.
Simply because probably the federation is a group of large companies that make money in some other ways.
And also, even in the case that you were describing, right? Using the moment of low fee rate due to the market. How much of a difference are we talking about? 10%, 20% in the fee rate. It's not the main point of this. The main point of this is suddenly the fee rate spikes to 100 sats per VByte, right? Or 200 like it has happened, and someone tries to claim, or we need to sweep up pegging, there is 100,000 sats. It's gonna cost a lot of money, and it ended up basically being completely detrimental. If you pegged in at 100 sats per VByte, right? And suddenly you need to sweep at 120.
Yeah, but last things. Usually, as Bitcoin is designed, I expect the fees going on with the years always to grow.
Yeah.
So your assumption, of course, looks at a little time window, so it's not really important to the fact that the Bitcoin's fees grow in the years. But maybe there could be in the future a moment where somebody pegged 10 years ago into Liquid.
No, that's the point. Okay, now I got what you were missing. So let's go back to the sweeps. Liquid takes every transaction, and in order for it not to be usable by the emergency keys, everything is swept within 4 weeks.
Okay, so you refresh the transaction.
Exactly. Exactly. So I know that the assumption is that the fee rate is going to be the same. We know it's going to be the same.
In 4 weeks.
Exactly.
Not something bad.
Exactly. So yeah, that's exactly the point. It's basically everything is swept within 4 weeks. I think we are going to move it to 8 weeks soon, but still, it's not something that we think it's going to be that meaningful. And even with that, the protection that it adds, it's good enough. And from the usability perspective, it's much better if the user knows exactly what the number is going to be when they create the transaction on the Bitcoin side, because the fee rate is going to be analyzed based on that transaction.
They know what the number is, and they know that they can update that for weeks, because this number needs to change. The user will not pay the same amount for weeks.
No, the user, so let's say that you create a transaction to do a pegging. That transaction paid 4 sats per VByte. When you claim it, Elements is going to say, okay, that transaction paid 4 sats per VByte in Bitcoin. So what I'm going to do is I'm going to look at how much is it going to cost the network to sweep that transaction at 4 sats per VByte. And that is the amount that is going to be discounted from your claim. So it's going to be fully deterministic at the time that you created the transaction in Bitcoin.
Okay. I probably need to look at the formula to stabilize my mind, but I will do later.
Yeah, but basically it's fine. The easy math is we always assume that it's basically 400 bytes per UTXO. So if you peg in at 1 cent per rebyte, the discount is going to be 400 cents. If you peg in at 4, it's going to be 1,600. So the math is not literally that, but that's roughly the idea. So you know exactly what the discount is going to be the minute you created your Bitcoin transaction. It's fully deterministic all the way through. So, what time is it?
You have 2 more minutes before the original.
Oh, shit. Okay. Okay, this is getting longer. So, one thing that is not there is the ELIP 203, which is the hard fork that I was mentioning earlier, the idea of removing the 21 million limit for issued assets. Okay. And there's another one that is still in draft, which I think is ELIP 204, which is what we call multi-asset fees, is the idea that is not yet approved or not confirmed, but the idea to be able to pay for transactions in pay for the fees in assets that are not LBTC. let's say that, for instance, someone wants to do a Tether native network, and they don't want to pay for fees in LBTC, they could pay for fees in USDT. Just a theory, just an analysis, but it's something that we are studying with the federation to see if it makes sense to do or not. Okay, let's go to developer tooling. There's a lot of, basically an introduction of the type of tooling, a lot of the things that Seth is gonna use during the rest of the process. Wallets. There's a lot of ways that you can create a wallet in Liquid, but it all goes back to the same way that you can use in Bitcoin. You have different software wallets, hardware wallets. You have Bitcoin D in Bitcoin. You have Elements D with the Elements CLI. So I think the most important one is here. Obviously, the Blockstream app. I need to I need to mention ours, right? I think many people use Aqua. It's a really nice wallet. LWK CLI, which is something that Seth is gonna use, the LWK, and liquidwebwallet.org. Liquid Web Wallet is a fully functional wallet. It's horrible because it's supposed to be a demo, but well, Ricardo's not here. I can say horrible. Yeah, it's not for. About it actually being a pretty wallet. It's a way to test the integration between LWK and WASM, so that you, in theory, you can do a full wallet on a web browser that is actually connected to a hardware wallet, like the blockchain trade. So for testing purposes, it's amazing because you can do a lot of things from within a browser. Low-level libraries, and I always say it, I have to say this, SecP 256K1 CKP. it's a hard tongue twister. But that's basically, in Bitcoin you have libsecp, which handles a lot of the cryptography. In Elements, you have the CKP, the zero-knowledge proof version of the same library. And just as Elements is based on the source code of Bitcoin Core, the CKP library, the CKP version of libsecp is based on the Bitcoin version of SecP, sorry. You have libwally, the wally as in wallet is a library to make wallet, Rust elements and elements miniscripts, which are basically the elements versions of the Rust Bitcoin and Rust miniscript. Liquid.js, it's being used less and less now, but it's a full abstraction layer for accessing Bitcoin, for accessing Liquid through JavaScript. Now with the bindings from LWK, people are starting to use it less. Backends. What do you use to get access to Liquid or to any Elements chain? Elements D, just like you use Bitcoin D on any network. If you on Bitcoin, you can use the RPCs that are basically the same as in Bitcoin. You can use the Blockstream Act backend if you use the old 202 multisig. You can use Electrum or Explorer. Anybody has used Blockstream.info or mempool.space. Or you can use Waterfalls, which is it's a backend that is similar to Explorer, but much more optimized for descriptors. So you basically, in Explorer, you need to pass every single address to the backend to get all the transactions. Waterfalls, it's another type of backend that supports passing the descriptor with all the privacy implications that it might mean, but it lets the backend do a lot of the work, so the work on the client side for the wallet is much less. Basically, you can run your own block explorer. The code is open source. I don't recommend it because it's a resource hog, but you can run your own block explorer.
I mean, with a simple explorer, I could see every federation created on Liquid. Or
Liquid is one federation.
sorry, on elements that
You can install multiple instances of a block explorer pointed to different chains, which is literally how the block explorer works, because you can point it to Bitcoin, you can point it to elements, you can point it to Bitcoin testnet, or you can point it to elements testnet. It's 4 different instances, but it's literally the same protocol.
Okay.
So SDKs, in order to work with Liquid, GDK, we don't recommend people to use it anymore. It's the old way of doing things. LWK, Liquid Wallet Kit, is basically where we are developing all our future resources. The idea is LWK is written in Rust. It has, you can use it either as a library or as a fully fledged wallet, which was behind Liquid Wallet Kit, Liquid Web Wallet, as I was mentioning earlier. And the most important thing about LWK is that we do bindings for a lot of languages for it. So even though it's written in Rust, you don't need to be writing in Rust in order to use it. There are bindings for Python, Go, Wasm, React, React Native, and Java, and whatever. So the idea is that we centralize the development in Rust, in LWK, and then anybody who needs to use that, they will use exactly the same implementation regardless of the language, which means that every part of the ecosystem is much more consistent with regard to support. Yeah, we don't want to talk about GDK. Yes, I was mentioning earlier, LWK, we wrote it like 2 or 3 years ago, with a much modular approach, and all the new features that we're being adding, including the simplicity stuff that Seth is going to talk about, all of that will either was added or will be added to LWK to simplify all the access to Liquid integrations. With regard to signers, classic, any software signer like Blockstream wallet, any software signer, you can use the hardware wallet like the Jade or Ledger, quote unquote Ledger, because supposedly we built an app so that Ledger can be used on Liquid. It's waiting on their approval for like a year, so hopefully we will have it soon. But yeah, it's there. As I was saying, the languages that are supported by the bindings. Let me see. Okay, only one. Okay, asset registry, last one, I promise. As I mentioned at the beginning, you can issue your own assets on Liquid, but from the chain perspective, an asset is just a hash. There is no information. Nobody knows who issued it. Nobody knows absolutely anything about it. So the asset registry is a service that Blockstream provides on top of Liquid, where you can register your own asset so that wallets can pull information from that assets and get extra, like getting an icon, getting the website to the issuer, or things like that, which is basically, if anybody uses the Blockstream app and gets some USDT or even on Aqua, you can get all that information. All that information comes from the asset registry. The thing is, you can attach a hash to the asset creation, right? And that hash can be used to validate that the information provided by the registry is correct. So you create your own, let's say that you create a JSON file that says, hey, this is my website, this is these are the conditions for this asset, whatever. You can associate that with the asset creation, so the asset registry will provide the wallets with that information so that it can be used and can be interpreted in the future. Simplicity, I'm gonna leave it to Seth. And yeah, some links, and that's the end with what?
Oh, it's 38.
38, 8 minutes late. It's not that bad. It's all his fault, but whatever. We don't need for you guys to have a Liquid testnet node. He adapted the presentation so that you don't need to, but I left a thumb with all the blocks from the Liquid testnet network. So if you want to run your own elements and with Liquid testnet to play later, you don't need to do a full IBD. So I have all the blocks so that you can basically copy them and have a full node running in a few minutes. Okay, that's it. Thank you.
Do we have questions for you?
No. Okay. I think now we're gonna cut for lunch, and then he's gonna attack you later with all the simplicity stuff.
Yeah, so we'll be back in the afternoon, and I have a whole presentation about simplicity and simplicity development for smart contracts on Liquid. I think according to our schedule, we're going to go from... Did you want to talk about the schedule and the lunch arrangements?
Yeah, right. Hey guys, we have a lunch near here in Norman, so it's very cool. We have about an hour. The menu is fixed because we are a lot, so they didn't want to give us choice, freedom. And yeah, we'll be back in an hour, so we can go all together there. Let's just group in the ground floor, and then we can go.
Okay, I think I'm going to announce the start of the afternoon session. So once again, thanks to everybody for being here. It's really great to have you here and great to be here to talk about simplicity. So I'm going to be talking about our smart contract technology that runs on Liquid, as you heard from Pablo earlier today, this morning. I did have a notional schedule. I think we're about an hour behind the schedule because we took a properly relaxing and enjoyable lunch. I'm going to hope to try to finish up by 6, the time that we had intended, which would give me about 4 hours, but I also have promised to have a coffee break about halfway through. So I think I'm going to be presenting here for about 2 hours and then have a coffee break and then present for about an hour and a half. That's my hope. So I hope you'll find it fun and interesting. So I'm Seth. I work at Blockstream as the Simplicity Developer Advocate. So I'm here to help all of you learn and make use of and benefit from simplicity, and find out from you what you'd like to see in simplicity and what you need in order to make use of it. This is the 3rd time that I'm doing this, but the first 2 times that I did it were in my first couple of weeks at Blockstream. So I was quite new to simplicity at that time. It's been about 6 months now that I've been working at Blockstream in this role, working with simplicity on the simplicity team. And I'm quite proud of what the simplicity team has been accomplishing. It does mean that there's a lot more to show and a lot more to talk to you about. And so I'm conscious that this is despite the name, a fairly complex technology, a fairly involved discussion, and also a fairly large developer ecosystem. So I'm going to talk about a lot of tools, some of which didn't even exist the prior time that I presented this. So we have a lot of options and a lot of tools that we're creating to help you develop with simplicity. But that also means more obligation to stand here and say, well, we have this, and we have this, and we have this, and we have this, right? Anyway, so I think we'll just have time to have a little taste of some of these things, to show you some of the documentation, to show you a few examples. What I have in mind is to demonstrate and talk about simplicity for a bit, including showing a few contracts running on Liquid testnet, showing you some of the code, showing you what it looks like, giving you some idea of how it works. Then I have a bunch of material about concepts and design patterns that come up in this context about how Simplicity works, how it's integrated into the blockchain environment, things that are helpful to understand in developing your own contracts and developing applications based on them. I have notional times and amounts of time that I had planned, but again, we're a bit behind and these may be kind of imaginary as it may turn out. And then I want to talk a bit about some of the developer tools and things that we have to help you build applications on top of this. And then at the end, I have a potentially interactive session where you can try to follow along and try to basically recreate some of the demos. So we've created something called a GitHub code space. This is a form of what's also known as a dev container. So for the last session at the end, I have in mind that those of you who have laptops handy could open up that dev container and you can run some of the demos yourself. And I can talk about what they're doing and what you're seeing. Again, that's at the end. So we'll talk about some of the conceptual stuff and you may see me demonstrate it before then. Please do feel free to ask questions. We're here for you. We want to find out what's clear and what's not clear, what's helpful and not helpful. As I think you all know, we have this space again tomorrow for a hackathon. We do have prizes for the hackathon, and we have a page up for you to register teams. You're also just welcome to come, even if you don't want to create a hackathon project and don't want to compete. You're welcome to just come and try things out and ask questions. But if you'd like to formally enter and consider submitting a project, that's great too. I'll talk a little bit more about that also at the end. But again, that's all day tomorrow here. Great. Oh yeah, I'm not expecting to announce winners in person here because I think we're going to have submissions at the end of the day. And then I'm expecting to go back to the United States and I'm expecting to talk about it with my colleagues. And so my plan is that within about a week, we'll announce on social media and by Telegram who the winners are. So I'm sorry not to have a prize ceremony here, but I don't think that the schedule really cooperates with that on this occasion. Okay. I may be turning back and forth quite a bit because I have some interactive demos where I'm going to have to show them up on the screen. But Simplicity is a technology that Blockstream has been working on for quite some time. And it's a smart contract environment. And it occupies a role very similar to that of Bitcoin Script, which many of you will know is the native scripting environment for Bitcoin transactions. And conceptually, it, like Bitcoin Script, can run natively on a blockchain and let us build various kinds of financial products and services on top of that blockchain. And in comparison to Bitcoin Script, it's a lot easier to read and write, and also a lot more expressive. And it's able to do certain things, and I'll give an example extremely soon, that Bitcoin Script really can't do. So again, it's going to be occupying a similar role in terms of writing spending conditions for blockchain assets, describing circumstances under which blockchain assets are allowed to be transferred. But it's going to let you do so in a much more expressive way than Bitcoin Script traditionally does. Simplicity also has a design philosophy that really emphasizes safety and correctness. And we have a lot of interest in formal verification to help check and to help prove that contracts do what's expected. As of right now, we don't have many formal verification tools that work on Simplicity contracts. So we have a lot of formal verification of the Simplicity interpreter itself in terms of confirming what the Simplicity interpreter does and what it's meant to do and what the Simplicity language is meant to mean. And this is basically a foundation in the long run to help us write other verification tools that will help verify things about the behavior of contracts, with a focus on security to mitigate contract bugs that would result in the loss of value, which is a problem that's existed a lot in the smart contract space. So I wanted to show an example right away with a real contract. And the example that I have in mind to show you right now is one that I wrote. I call it third time's the charm. My Italian pronunciation is not very good, but this is apparently equivalent to la terza volta è quella buona. So something works the third time you do it. In this case, this is a vault contract. So a vault contract is a form of blockchain contract that intentionally makes it slower or harder to withdraw assets. There are many reasons you might want to do that for security. This contract doesn't really provide a useful security benefit because there's no time delay in these 3 requests. And there's no way to cancel the withdrawal. You just have to ask the contract 3 times, and then it lets you withdraw assets. However, I like this example because it's something that we can't really do with Bitcoin script, because this is going to control assets across 3 different related transactions. So in Bitcoin script, typically you can only directly control the disposition or the transfer of assets in one single transaction. And then the assets are no longer under your control as the developer. In Simplicity, we can implement these covenant patterns, which I'll talk a lot about, in which a smart contract can require that assets are sent back to that same contract, possibly with some kind of state update. And so the assets remain under control of the smart contract, even across multiple transactions. And this vault is a concrete example of that, right? It says, okay, some assets are held by this contract. You can withdraw them, but you have to first make one transaction. Then you have to make another transaction. And then your third transaction, and only your third transaction, is allowed to withdraw the actual value. Right, so you're going to actually see 3 different on-chain transactions, which are all interacting with the contract. And you could imagine making something actually practical where you have a multi-step withdrawal, where multiple transactions that are meaningfully different and distinct from each other need to happen in sequence. And for example, there might be someone who could intervene and say, actually, I don't agree with this, and cancel it and set the state back. So that could be a practical use of a vault. Yeah, so if you were doing this in the, just opening a terminal here, I hope. Yeah. Okay, I'm going to have to turn back and forth here because I don't have screen mirroring going on. And I may switch to using this microphone as well. Okay, so this is going to display quite a lot of technical information. And so we have this perennial difficulty about demos about how verbose they ought to be. This demo is extremely verbose. So you're going to see a lot of the detail. But basically what you're going to see is that we are going to take a SimplicityHL, and I'll talk about what that is in a moment, smart contract program. We're going to compile it. We're going to get a blockchain address on the Liquid testnet. We're going to ask the Liquid faucet, which is used for testing and which sends you Liquid test coins, and say, please send some coins to this contract and tell it that we've requested to withdraw them 0 times. Then we're going to perform a transaction with that contract where we say, okay, take the assets held by that contract, send them back to that contract, but let the contract remember that we've now tried to withdraw them 1 time. Now we're going to make another transaction, send those same assets back to the contract again, but let the contract remember that we've now tried to withdraw them 2 times. Finally, we're going to make a third transaction where we withdraw them entirely, and they're no longer under the control of the contract, and they're sent elsewhere. And if we were to request that earlier in the process, the contract would refuse. It would not let us make the withdrawal. So that's the concept here. And again, this is something that we can do with Simplicity relatively easily that we wouldn't be able to do with Bitcoin script. Okay, so we have a lot of different technical parameters here. We have a particular destination that we want this to withdraw to. We have a particular smart contract that we're compiling. And we have a private key that we sign to indicate that we're an authorized party. Now, the private key here is the number 1. So it might not be the most secret private key. But we could do this with a real random private key, just as easily. Okay, so this is the compiled version of the smart contract. I didn't show you the source code yet, but I will in a moment. But this is the compiled code. Having compiled it, we actually derive an on-chain address for the contract. So that address represents the logic of that particular smart contract. And that address can receive assets. And if you can satisfy the contract, it can also spend assets. It can send them elsewhere. Or in this case, it can also send them to itself. And that's what we're going to do at first. Okay. Now, an interesting thing here is that we've actually determined in advance 3 different addresses, and you can see that the address changes here. These different addresses correspond to different states of the contract. So I mentioned before that the contract is going to remember how many times we've asked to withdraw. So we can actually pre-compute with this contract what the address is for a copy that believes you've attempted to withdraw 0 times, for a copy that believes you've attempted to withdraw 1 time, and for a copy that believes you've attempted to withdraw twice. And each of those has a different address, fundamentally different address. So both the code and the state are represented in the on-chain address. And so, as a kind of spoiler for what's going to happen, the faucet is going to send the test coins to this address representing 0 withdrawal attempts. The first withdrawal attempt is going to send the coins from this address to that address, meaning from a copy of the contract that believes you've tried to withdraw not at all to one that believes you've tried to withdraw once. The next transaction is going to send from this address to that address, from a copy that believes you've tried to withdraw once to a copy that believes you've tried to withdraw twice. And then the final withdrawal is going to spend from this address to an address of our choosing. And the contract logic itself can recognize each of these as the legitimate successor of itself, which is pretty cool, and which is an important concept of simplicity covenant programming. The ability for a contract to say, that's me. That's a version of me, but with something changed according to my own rules. And again, I'll show you the actual code that does that. Right, but that's what we're accomplishing here. So from the faucet to here, from here to here, and from here to here, and then from here we can withdraw. Okay, so we've received coins from the faucet. Now we're doing the first time, right? A lot of technical parameters. So we're building here a transaction. This is a liquid transaction. It sends coins from one address to another address, as I mentioned before, from the address representing our contract where we haven't tried to withdraw to an address representing our contract where we have, right? We include a digital signature. Having included the digital signature, we now finalize the transaction. And we get a transaction that we can submit to the blockchain, and we do, and it's now on the Liquid testnet blockchain. Okay. So now we're going to do it again. We're going to do the second transaction. Again, lots of details about how we build it. Right. Now in this case, it remembers that we've tried to withdraw once, And we tell it, hey, we've tried to withdraw once. How about if we try again? And we build a transaction that accomplishes that. And this is the transaction for submission to the blockchain. Now it's submitted, present on the Liquid testnet. And now we're doing the third time, which is the withdrawal. So we're saying from that last address, we're going to make a transaction that sends the coins outside of the contract. We build that up, we include a signature, we tell it, by the way, we've tried to withdraw twice, which means that we're now entitled to actually send the coins elsewhere. And the contract agreed with us and sent the coins elsewhere outside of the contract. So again, I'll show you the code coming up, and I'll talk more about some of the details about how that was implemented. But that's the kind of thing that we can do with Simplicity that we couldn't do with Bitcoin script. We can actually keep assets of various kinds. We can actually remember history associated with those assets. We can actually remember different facts about different parties and what those parties are or are not allowed to do. And that can change over time, all while the assets remain under control of the contract. Okay. So coming back here. Right, so I have also a diagram showing those related transactions in a block diagram. So let me pull that up too. This is just a block diagram of the same process that I just showed you. So we have the faucet, which initially holds a bunch of test coins. We have a deposit transaction where it sends it to a version of the contract. Where the counter is equal to 0, then we have an update transaction where we send it to a version of the contract where the counter is 1, another update transaction where we send it to the same contract where the counter is 2, and a withdrawal transaction where we send it to a user's wallet. And each of these arrows is actually an on-chain transaction on Liquid that's recorded on the blockchain. And each of these has some form of entitlement check and logic check to confirm that it's actually allowed to occur. So I said before, if we tried to make the withdrawal at this point, the contract logic would say you're not allowed to make a withdrawal at this point, and it would reject it. Okay, I want to be full screen again. Can I be full screen again? Not totally. Okay. I think I need to click the presenter view again. Sorry about that. It's going to be tricky to switch between these things, I think. All right. I wanted to show you some of the actual source code for that contract that I just ran. So you can see what some of the SimplicityHL source code looks like. Okay, so let me pull that up. Looks like that's the biggest font size that I can choose in my terminal, so I hope that's large enough. I know it may be a little tough in the back. Right, so I have a bunch of comments in the beginning talking about how it works. So I'm going to scroll down below. Right, so one thing you can probably notice is that it looks quite a lot like Rust. If any of you are Rust programmers or you've had exposure to Rust. So this language is called SimplicityHL. This is the high-level language for simplicity. And the syntax is directly modeled on the syntax of Rust. So we've tried to make it very readable for from the point of view of Rust programmers. Right, so we have function definitions here with fn, and then we have data types. We have parentheses and brackets like Rust, right? And so we're able to write this high-level logic in a high-level language, and we're able to define various functions, and then we can call our own functions. And a really important thing that we do, which turns out to be, in a certain sense, the most important thing that we do, is that we make assertions. And the assertions are enforcing the actual logic of the contract. Because the thing, and I'll also discuss this more later, the thing that this program is doing is deciding if a proposed transaction is allowed or not. So the assertions are describing the conditions under which the transaction is permitted. So they're really very important. So for example, here, we assert that the transaction has exactly 2 outputs. So because of this line, if we made a transaction with this contract that had 3 outputs, it would inherently be rejected. This assertion would fail, and the transaction would not go through. We also assert that the second output is a fee output on Liquid. Right. And then we have digital signature verification. This is the main function here. Right, and it's dispatching based on whether we're doing the update transaction, which is the first 2, or the withdrawal transaction, which is the final one. So it's quite Rust-like. There are some differences. I have a page about differences from Rust. There are things that you can do in Rust, but not in SimplicityHL. And SimplicityHL is compiled down to low-level simplicity that's interpreted by Liquid nodes. If you're running Elements D yourself, Pablo suggested in the morning, you could have your own copy of Liquid on your own laptop. You would actually be validating simplicity transactions, just like you're validating other transactions, by actually running the programs and confirming that they in fact approve the transactions. So every Liquid node is validating this by running the code. Our intention is for developers to write this kind of high-level code in SimplicityHL and then compile it down to our low-level representation, which we call simplicity, which actually runs on the chain. So even for things that we can already do in Bitcoin script, like we'll have a multi-sig example later, you can do that in Bitcoin script. The SimplicityHL version is generally going to be a lot more readable, a lot clearer what it's doing, and a lot clearer how to extend it. Okay. Right, so just to review what we just saw, that contract that I showed you is able to hold assets. You can send assets to it, and then they're actually held by the contract. The contract actually decides the conditions under which they can be transferred. It can enforce rules across multiple transactions, not just one. It can keep track of the history. So it can remember things like how many times an event has occurred. The only thing that it does, and I'll talk more about that, is it says yes or no to transactions that someone else proposes. It says, does this transaction follow the rules, or does this transaction not follow the rules? And as you saw, the identity of that code, as well as its internal state, are represented directly in its on-chain address. So if we have a different contract, it's going to have a different address. If we have different state, it's going to have a different address. That's all encoded by hashing into the address. So whatever contract you write, it's going to compile down to a compiled representation, which is going to derive an address. And then you can send assets to that address, and then they're controlled effectively by the logic of your contract. Okay, so I hope it's not impolite to ask if any of you are coming from an EVM or Solidity background. I know that some people who registered said that you had prior experience with EVM and Solidity. So there are a lot of big architectural differences between the on-chain model for EVM and Solidity and the on-chain model for Simplicity. I'm sorry. Yeah, so I want to say one really key point, which is not just true for Simplicity, but is really true for all Bitcoin-like blockchains all the time. Every single asset that exists on the blockchain is always present inside what we call a UTXO, an unspent transaction output. That's the only place that an asset can exist. And a transaction consists of transferring assets from some UTXOs to other UTXOs. None of that is changed by Simplicity. That's true for Bitcoin, that's true for Liquid, and it's still true in the Simplicity context. Similarly, every UTXO always has conditions for how and when it can be spent. So it has some kind of rules for if you wanted to move the assets that are in this UTXO elsewhere, what would you have to do? In classic Bitcoin, that's most often a digital signature, but it theoretically could be more complicated things that are expressed in Bitcoin script. When you satisfy the spending conditions, you can make a transaction that sends the coins, that sends the assets somewhere else. That somewhere else is always a UTXO itself, right? Coins that are represented as controlled by someone's wallet are in a UTXO. Coins that are represented as controlled by a smart contract are in a UTXO. It's just a question of which UTXO and what spending conditions apply to it. And the spending conditions are always derived in some way from the address. So Simplicity adds new ways to provide spending conditions and to write them. And that's where Simplicity lives in Liquid. It lives in the context of creating and expressing spending conditions. And again, it does so more expressively than Bitcoin script. So Simplicity is pretty new in terms of the Liquid integration. Liquid integration was completed last year. People are building some cool stuff. I'm going to show the use cases page later that has links to some of these. But people are building some fairly sophisticated contracts. So we have examples, some of them from our colleagues at Blockstream, some of them from other people, with implementation of options contracts for options in tokenized assets, a prediction market that runs entirely on-chain with no trusted party. It does have oracles that are trusted to decide what happened in the outside world. Yep?
Yeah, I was thinking exactly about that. How from Simplicity I can interact with an oracle.
I have a whole section about oracles coming up, so I'm definitely going to talk a lot about oracles. So yeah, I'm glad that you're thinking about that, and we'll definitely talk a lot about that. People have also been implementing automated market makers. Our colleagues at Blockstream have implemented a lending contract that lets you borrow against collateral. So for example, you can deposit one asset with the contract. You can borrow another asset from someone else. And you promise to repay a certain amount, typically with interest at a certain time. Basically, if you do repay, then you get your collateral asset back. If you don't repay, then the lender is allowed to liquidate the contract or partially liquidate the contract and seize some of your collateral in lieu of your missed repayment. And all of the logic of that is implemented and enforced by Simplicity. So again, there's not a trusted party, it's just all living on-chain. It's all implemented on-chain. We can also do swaps without a trusted party. We can do a lot of other things. We're always very excited to hear about new things that people are coming up with and building on Simplicity. This is a version of the user interface for our lending contract, right? Just to show you, this has been implemented in a web page. And I'll mention some of the tools that were used to build this later on. But this is an end-user-oriented interface to the lending contract, showing different actions that you can take. And each of those, again, will be translated into on-chain transactions that represent the effect of taking that action. But it can be represented to the user in terms of financial details. And a common case here would be that you would put up Bitcoin as collateral and borrow money in a stable coin. But the lending contract doesn't make any assumptions about that. Could be any pair of assets. It doesn't have to be a specific pair of assets. And this is a mock-up of the mobile device user interface for the lending contract. So this is, again, meant to interact with the same on-chain contract, but it's actually the UI mock-up for the mobile interface, which, again, will then build on-chain transactions to interact with that logic. So we've been working on creating Simplicity for a long time. Our colleagues at Blockstream proposed it in 2017 in a context of a lot of thinking about smart contracts in the Bitcoin world and in the blockchain world more generally. Right, so a lot of people have worked with EVM and Solidity, which are very popular systems, which have also been plagued by a number of scandals and hacks where a lot of value has been lost, often because of relatively small bugs in smart contracts deployed on EVM. The DAO hack was one of the more famous ones that happened kind of right at the beginning of the smart contract scene on EVM, but there have been lots of other scandals since then. And one of the motivations for Simplicity was to create technical foundations for building higher assurance smart contracts that would be easier to reason about and that would be easier to prove and confirm properties of. So eventually we want to have tools that make use of formal proofs, that make use of type theory and type checking, that let you confirm certain assertions about the behavior of the contract in all circumstances. Anyway, we did roll it out last year on Liquid Network, as Pablo discussed. We're working on this year deploying it on a Bitcoin testnet to demonstrate a Bitcoin native version. We're also working on an Oracle-based mechanism for running Simplicity contracts on Bitcoin Core, where an Oracle would indicate the result of interpreting the contract. Okay. I think I actually mentioned this on a prior slide about everything being in a UTXO and Simplicity creating spending conditions for UTXOs. So it's just worth mentioning, it's a fundamental rule of the Bitcoin consensus and the Liquid consensus that every UTXO can only be spent once. A lot of Simplicity contracts are going to rely on the blockchain's enforcement of that property so that you can automatically distinguish between a UTXO that is in fact unspent and one that has been spent. The fundamental thing that the Bitcoin consensus prevents is double spending a single UTXO more than once. And so if we represent various things or assets as UTXOs, we can distinguish between whether those are still out there or whether they've been consumed. That can be a very valuable property for a lot of contract logic. And again, if you do send assets back to the same contract, which we call a covenant, that's going to create a new UTXO every time you do it. It's not that the same UTXO is somehow refreshed or replaced or anything. The original UTXO is spent and consumed and can never be spent again, but you may have a new UTXO that represents the further history of those assets with that contract. This is just a diagram representing this idea, that we have various UTXOs at some point, and they have various spending rules and conditions that apply to them, some of which may be written and implemented in Simplicity. And then we can perform a transaction with a witness. I'll talk about witnesses in a moment, where we say, I would like to consume these UTXOs and transfer their assets to a new set of UTXOs that we specify. And if the spending conditions are satisfied, then that's allowed to occur. And all of these old UTXOs are used up and no longer exist. And now all of these new UTXOs exist with some combination of the value that was present in the old ones. So a Bitcoin transaction, a Liquid transaction, a Simplicity transaction is basically a machine for turning some collection of old UTXOs, following some conditions and proof that you're allowed to do it, into some new set of UTXOs. Right, so I mentioned before that one of the important motivations for creating the system in the first place was safety. And I am going to mention in a moment the Turing completeness issue. One thing that we know from computer science is that if we have Turing complete programs, programs that can compute anything that a computer program can compute, we can't in general actually determine what they do. We can determine what some of them do, but we always have some programs and some forms of programs where we don't know what they do, where no particular procedure would actually answer the question or predict the behavior. And that fundamentally falls out of being able to write arbitrary programs with arbitrary loops. So in Bitcoin script and in Simplicity, we don't have unbounded loops, we don't have Turing completeness, so we get a property called decidability, where the outcome of every program can in principle be predicted. And this means, for example, we can't have any programs that run forever. We know that every program eventually stops. There's a lot of other emphasis going into Simplicity in terms of type theory work and formal verification work, using modern tools to write a formal specification that says, this is what Simplicity is about, this is what it's expected to do in all cases. And that creates a foundation for reasoning about what Simplicity contracts do and what they don't do. And as I said, eventually for making tools that will help to confirm claims that you want to make about a program, like assets can never get stuck in this program, or like this user always has the ability to withdraw assets, or this user always has the ability to withdraw assets under these circumstances. And we're starting to work on static analysis tools, which are the first stage in that process, that let you check and confirm some properties of Simplicity covenants in terms of understanding what the covenant does or doesn't constrain, and actually being confident by analysis of the code. This does constrain that, it doesn't constrain that, it enforces this, it doesn't enforce that. Okay, so we have a lot of focus in this area of correctness and automated reasoning. We also have this JET mechanism, I'll show you more information about that in a moment, that helps a lot with the speed and the efficiency, in which we have common functions that are implemented in native code. And so for all of those functions, you can call out to the native code and perform some task very quickly and very efficiently. And Pablo was talking this morning about how Liquid has a multi-asset mechanism, and how you can have your own assets that you create on Liquid. You can have assets that other people have tokenized. You can have a practically unlimited number of tokenized assets on Liquid. And Simplicity on Liquid is natively able to work with all of them. It's able to recognize which ones they are. It's able to enforce rules that require a certain asset, that treat a certain asset a certain way. Simplicity is also portable to other Bitcoin-like chains, and as I said, we're working on deploying it on a Bitcoin testnet to demonstrate what it looks like on Bitcoin Core. And I mentioned before that we have the high-level Rust-like language SimplicityHL, and you compile it to low-level simplicity, which is actually interpreted by the interpreter in the nodes. Right. Yeah, so I actually showed you that contract in the text editor before. So I think I may not open it up a second time because we've had a chance to look at it. I mean, I want to spend some time talking about the details of what it does and talking about the differences from Rust. But let's get back to that when we get to some of the later demos, I think, because you got a chance to see the syntax, basically. Right, so I also mentioned that simplicity is intentionally not Turing complete, much like Bitcoin script. So all simplicity programs eventually finish. You cannot have one that loops forever. We can actually determine some things in advance, like the maximum resource requirements for a program, which is pretty cool. So we can determine, for example, what's the longest amount of time that a certain program could ever take to finish. And we can know that at compile time, not just observing it empirically at runtime. And without Turing completeness, it is comparatively easier or comparatively possible to, in general, prove or automatically detect certain claims about the program's behavior when it's run. Right, so in a simplicity transaction, some user creates a proposed transaction and submits a proposed transaction that transfers assets from a simplicity contract, very often back to the simplicity contract, but potentially elsewhere. That gets submitted somewhere to a mempool, and then nodes run the contract logic, and they decide yes or no. They say that transaction is allowed or that transaction is not allowed. So there's a lot of stuff that we don't have that you would expect to find in other programming languages. So notably, we don't have any form of I/O, we don't have any form of user interface. We don't have any form of file storage or database. We don't have any form of network access. Your simplicity program can't call an API. We don't have any form of data access outside of the local transaction environment. So you can't make a query to a SQL backend or something. Okay. So we're really running in this very constrained environment where we're deterministically checking, is this particular transaction allowed or not? And that's really all that we're doing in the actual simplicity program. And I want to again emphasize this because a lot of you have done software development in other environments that are not quite like this. You may have written network services that run as a daemon that react to requests in general. You may have written clients that call APIs. You may have written programs that store things in a database. Right? In this environment, we're not doing any of that. We have to figure out how to describe things in terms of, is this transaction allowed? Just based on what we see in front of us right now. We do have state commitments. So we do have an ability to say, in the address of our contract, I remember certain facts, and if someone reminds me of what those are, I can confirm that they match what I expect them to be. Right, but that's different from an external database. It's different from a database that's maintained or updated by someone else. And I want to mention, the simplicity contract itself is never initiating any actions. It's only responding to transactions that are being proposed by a party. So someone else with some kind of software, some kind of wallet, some kind of app, is coming to the blockchain and saying, I would like to spend this, I would like to transfer this. And simplicity says, okay, you are allowed to do so. Or it says, sorry, you are not allowed to do so. The simplicity contract never sort of wakes up and says, oh, it's Tuesday, time to send that money there. Rather, on Tuesday, a person can come and say, I would like that money. The simplicity contract can say, okay, it's late enough in the future that you're entitled to it. I'll approve your transaction. So this means that when we create these financial services and these financial tools, we're really going to have to think of their logic in terms of on-chain states and in terms of transactions and in terms of permissibility of transactions. Question?
Do we have access to random number generators or something like that?
Do we have access to random number generators? We do not have access to random number generators. The simplicity contract execution is deterministic, so everyone has to get the same result. One traditional way to simulate random number generation in Bitcoin is with hashing. If you have some relatively unpredictable in advance thing, then you could hash that thing and you could use the output of the hash as a pseudo-random number, as long as it's something that's publicly visible to everyone, so that everyone would get the same result. So I think the Satoshi Dice gambling game, for example, did that to decide the random outcome of gambling. It was basically cryptographically hashing something that wasn't exactly under its control. I don't remember what the actual data was. And then looking at the result of the hash and saying, well, this was unpredictable. But it's not random in the sense that everyone who does it gets the same answer. Simplicity is the same that way. Okay, I have this metaphor. Some people have found this metaphor helpful and some haven't, so I hope that some of you will find it helpful and be in the I like this metaphor crowd, right? So a possible metaphor is thinking of a sports referee. Now, the reason that I mention the sports referee is that the referee is not a player of the sport. The referee is not on the field actually kicking the ball around. The referee is not trying to score points. The referee is not saying, let's do this, right? The players do something. The referee just sits there in the background and occasionally says, okay, you were allowed to do that according to the rules of the game. No, you weren't allowed to do that. That's not okay, right? The referee doesn't make the rules. The referee doesn't make the plays. The referee just says, according to my knowledge of the rules, you're allowed to do what you did. That point is valid. According to my knowledge of the rules, you're not allowed to do that. That point is not valid. Also, you can't convince the referee to change the rules in the middle of the game. They're written down ahead of time, right? You're not supposed to show up and say, well, I think that football would be more fun if we had this other rule. Why don't we introduce it, right? And so in this analogy, the rules of the game are set by you as the smart contract developer ahead of time, before anyone begins to interact with the contract. And then Simplicity as the referee is going to very objectively enforce whatever rules you set. And whatever parties are allowed to interact with that contract by creating transactions can then come and follow whatever rules you wrote down. And the referee is not going to say, I like that rule, I don't like that rule. The referee is going to say, those are the rules. The developer wrote them down. Someone tried to do something. I say, yes, that follows the rules, right? So again, you can decide whether that metaphor is helpful to you or not. Obviously, it's more deterministic than a human referee, right? Human referees might disagree with each other. Simplicity implementations, since simplicity is formally specified, should really not disagree with each other about the legality of a certain transaction. Okay. I think we're going to go for about half an hour and then have our coffee break. I hope that's okay for people. I have a few more things to discuss and show here. So I want to mention the concept of witnesses. Some of you, if you've worked with Bitcoin script or other languages that create Bitcoin script, may have encountered the witness phenomenon and the witness terminology already. So this is a term that was borrowed from computer science. And in computer science, a witness is an example that shows that a certain property or set of properties can be satisfied. That there actually is something that follows these criteria. Now in simplicity, and again borrowing this term from Bitcoin, the witness is essentially the input to a contract. So if you're building a transaction, if you're one of these parties, you're interacting with this contract, you're saying, I want to spend something, I want to transfer something, you're going to give as part of your transaction a witness, which is whatever data the contract expects that would help it to decide whether you're allowed to do that. The most obvious example is that you might give it a digital signature. The contract might say, whoever has this key is allowed to move these coins. Well, in that case, you're going to need to give a signature made with the appropriate key in order to confirm that you're an authorized party and you're allowed to move the coins. But it could be lots of other things. And whatever the contract says it wants to see defines what kind of witness should be given to that particular contract. Yeah, so we typically write the witnesses for SimplicityHL in this JSON notation. Now, some of the tools that work with Simplicity contracts actually don't require you to make this file. So this JSON data we call a .wit file, and this is the most traditional notation for witness data for Simplicity contract. But if you're using some of the tools, they may not actually require you to write this as JSON. You're still going to have the same data in the same structure, you just may not have it on disk in a JSON file. You may build it up yourself with some API calls. Okay, and so the witness basically consists of a bunch of values requested by the specific contract, each of which has a name and each of which has a data type. This is an example of a witness that would be given to a certain covenant that we have called the last will covenant. Let me show you that one. Let me show you a diagram of that one. Cool, so this is an example that comes with the SimplicityHL examples, and I can show you also the SimplicityHL code that implements this, but this is a diagram of the logic of the last will. Okay, so this is something, again, that we can build with Simplicity that would be hard or impossible to build with traditional Bitcoin script. And this is a mechanism where someone who has a blockchain asset like Bitcoin can say, I want a certain person to inherit this if I die. I want the person to inherit it automatically if I die, right? So obviously if I die, I can't really then take an action to indicate that someone should inherit, so it has to happen without me. Okay, so the last will covenant, again, we have an implementation of this, we can look at it, we can see how this is expressed as code. But there's the person who creates it, and the person who creates it deposits assets with the last will. And then there are actually 3 different actions that can occur. One is the creator can say, actually, I changed my mind. I want to take this money back out of the covenant and just have it again. And that uses the cold key, which that person might keep offline. That might be a more sensitive action that doesn't need to be taken routinely. And so that could use a key that's not stored online, that's not easily accessible. But basically, if you change your mind, you say, I want the money back, it says, okay, well, you're the person who created it, it's your money, you can take it back. There's another action you can take with your hot key, which is a key that you may have online to use routinely, where you say, by the way, I'm still alive, meaning I don't want this money to be inherited yet, because I haven't died. So I'm still around. And in that case, you're going to take the assets from this contract and send them back to the contract in such a way that the contract is aware that you were active recently, and therefore that you're not dead. And so by default, you're asked to do this at least once every 180 days. We can change that number to any other number, right? But every 180 days, you're asked to make this transaction, send these assets back to the contract.
This is kind of like a simplicity version of what we were talking in the morning about how the wallet in Liquid behaves with all the assets. Basically, sweeping the Bitcoin side of the wallet means the network is not dead. The network is still working. The emergency keys should not be used. It's the same case.
Yeah, it's a very similar pattern. And so then there's a third action, which is the inheritor, using a different key, can make a claim that is, I think the creator has died. The assets have not moved in the past 180 days. Can you please send them to me? Okay? So we have those three different actions that you can take. The creator withdraws the assets. The creator says, I'm not dead, and sends the assets back to the contract. Or the inheritor says, I think the creator is dead. You can see that this hasn't been refreshed recently. Please send the money to me. Right. And again, we can look at the code for that. I mentioned this as an example of a witness. Each of these actions, the logic of the will is going to require a certain form of witness to confirm that that action is allowed to occur. Okay? One part of that is just which action is it? That's part of the witness. Are you trying to do this? Are you trying to do this? Or are you trying to do this? That information is in the witness. Then if you're trying to do this, the question is, okay, can you show me a signature over your transaction using your cold key? That goes in the witness. Here, if you're trying to inherit, okay, can you show me a signature over your transaction with the inheritor key? That goes in the witness. How about here? You're trying to refresh it. Can you show me a signature over this transaction with the hot key? Right, so in each case, the witness is going to indicate to the contract, which action am I taking? And here's a signature that confirms that I'm allowed to take that action. And so this example is an example of the witness that that the inheritor would provide, that says, I'm the inheritor, I think the creator is dead, I want you to send me the asset. And we can look at the SimplicityHL code and see how this is interpreted. But this is going to correspond to code that consumes this input and uses it to confirm that the condition is met. I wanted to talk a little bit about jets, which are pretty important. So we are creating a standard library for simplicity. The closest thing to a standard library that exists currently are these jets, which are sort of like optimized standard library functions because their implementations are in native code that actually runs on the nodes that are executing the simplicity programs. And so they provide fast implementations of common tasks. One example is EQ32 to compare two 32-bit numbers to see if they're equal. Multiply 64 and multiply two 64-bit numbers. Current index and output amount are examples that do what we call introspection, where we're actually examining details about the inputs and outputs of the currently proposed transaction. Now, those are kind of special because those are things that can only be done by jets. So it's not just that they're efficient, but it's also that they can actually see the transaction environment. They can actually look up the details of the transaction environment. You wouldn't actually be able to look up the output amount if you didn't call that jet. But if you call that jet, you can find out, for example, for output number 6, what is the amount? And what is the asset that output number 6 claims to have? Here's another example that performs a digital signature verification of a Schnorr signature. That's pretty fundamental. Contracts need to verify digital signatures quite a lot. That's a jet that handles that. Excuse me. And then there are various SHA-256 related ones for creating a SHA-256 hash, feeding data into it, and getting the hash value at the end. And that's something also that gets used quite a lot. And it's really good to have those in jets because that would be quite laborious to code in your own program. But we can call out to those jets and SHA-256 will get calculated for us. Right, so these are a few examples of some of the things that jets can do. Logic, arithmetic, numeric comparisons, this introspection, looking at details of inputs and outputs, digital signature verification, cryptographic hashing. There are about 400 of these jets. I wanted to show you the list. I'm not going to actually read it off to you. We'd be here for a long time. Just want you to see where you can go to look up what jets exist and what they do. Great. So this is, and we have quite a few pages which I would love to have you look at. I wrote quite a few of these. On the Simplicity docs page, I'm going to give a link to that later on in the resources section. This is the JETS reference. So I said there are about 400 of them, right? This just describes a few of the different purposes for which JETS are used. And this is a complete list. So we have this, can people read this? I should probably make it a little bigger. That's a lot bigger, right? This is bitwise logic of various kinds, right? There are a lot of jets that deal with bitwise logic. This is arithmetic, right? Integer arithmetic. Hash functions, I mentioned that there are functions that help you compute SHA-256. Right. Elliptic curve functions for dealing with elliptic curve cryptography in your contracts. A lot of elliptic curve implementations. This is this digital signature verification, which I mentioned, which is really quite important and is used probably in a majority of contracts because the majority of contracts have some authorized party who's identified by a public key, whose signature is required in order to take some action. And this is the function that verifies that key. Okay. A few Bitcoin-specific ones. Several related to digital signatures on Elements transactions and the Elements transaction environment and this introspection and, right, examining details of inputs and outputs. And those are also very important. For example, the third times the charm contract that I mentioned uses some of these to check that, at least for the first two transactions, the output is a copy of itself. That's how it knows. It calls some of these introspection jets, and it says, okay, output number 0, is it a copy of me? Now, the is it a copy of me is a few lines of code that uses various jets, but it's essentially output number 0, is it a copy of me? And it says, well, it has to be at this point. You have to send the value back to me. If output number 0 is not a copy of me, then the transaction is not acceptable. So that's basically the fundamental implementation of covenant logic. Okay, we have a lot of details related to Elements transaction environments. We have some related to time locks. I have a whole page talking about how to use time locks. So you can say that a certain transaction can't occur until a certain time. That's something that does exist in Bitcoin. It's something that's very useful. I'll have a slide actually about that. Right. I think Pablo was mentioning that you can issue your own assets on Liquid. You don't need permission to create a new asset or a new token. So there are many reasons that a Simplicity contract might want to issue an asset under some circumstances. And the contract itself can have the logic to issue the asset. And there are jets related to controlling that process. Performing a Liquid asset issuance, right? More introspection stuff. Sorry, there's a lot of introspection stuff. A couple of jets got deprecated because of an error, and that's going to be the end of our jets reference. Anyway, about 400 of these. They're pretty important for accomplishing a number of things at all, and in many cases for accomplishing things efficiently. Okay. Right. Yeah, question.
For confidential transaction, for example, can I check the amount of the transaction for confidential
So the question was about confidential transactions and can one check the amount using Simplicity? So this is a really great question. I actually want to write an entire documentation page about that question. Hopefully next month, maybe next 2 weeks, I'll have a page about that. Just at a high level, and I actually had a great conversation with Pablo about this exact topic, there are different patterns for how you use confidential transactions. So you can write a Simplicity contract that holds confidential assets without even knowing what they are, which is interesting. For example, the last will contract, you could actually send a confidential asset to it, and it actually wouldn't have to know what it had. It just knows that it controls something, and that someone can inherit that under some circumstances. So it never unblinds it. It just says, I'm the owner of this asset, now you're the owner of this asset, whatever it was, right? Another pattern is that you could have some contracts that inherently do need to know the details. Now, unfortunately, a Simplicity contract can't store secrets. The contract's logic, at least when it's spent, is always going to be published on the blockchain. So it can't contain a secret value that is not allowed to be disclosed to other people. So the contract itself can't unblind a confidential asset unless the asset is unblinded for everyone. So you can also have a pattern where you say, unfortunately, this contract needs to know the details because the contract itself can't store secrets. The owner of the asset must unblind it before sending it to the contract so that the contract can confirm that it's 3,000 sats of liquid Bitcoin, which otherwise would just be hidden and the contract would not be able to know if that's true. There is a third case. So confidential transactions in Liquid support creating proofs about claims about the underlying assets. For example, that two of them are equal to each other without revealing what they are, right? So this is a form of zero-knowledge proof. It's not fully general zero-knowledge proof for any claim, but certain kinds of claims like this asset is 3 times as much as that one, or these two are equal to each other. Things like that. You often can actually produce a proof of that without revealing the exact details. And there are several jets that are actually able to verify those proofs with a jet. So there might be some applications, for example, you might do some kind of currency exchange contract where you say there's an exchange rate between these two assets. And part of the condition for using the currency exchange is if this one is worth 3 times as much as that one, then the amount of this one should be 3 times as large as the amount of that one. In some circumstances, you could actually, in the confidential transaction system, create a proof that that's true without showing how much they are. And the simplicity contract could actually then use these jets to check that that's true. So I think that's pretty interesting. We don't have any demos of that. It's kind of a subtle use case, but I'm very interested in demonstrating that and documenting that. But I think those are basically the three patterns, right? The simplicity contract can hold assets without unblinding them, which can be useful if you just know that the ownership is the only thing that matters and that the amount doesn't need to be checked by the contract. You can require them to be unblinded, or you can submit proofs that about claims about them, right? Or for other circumstances, you say you have to deposit an equal amount, and then it can check that they're equal even though it doesn't know what it is, if the owner cooperates in creating the proof. Anyway, hope to have some documentation about simplicity and confidential transactions. Thank you for asking about that. So just to summarize about this covenant idea, which I've been alluding to quite a lot, again, because it's one of the things that simplicity fundamentally can do, that's really tough to do in Bitcoin-like blockchains traditionally. There are some kinds of contracts that are complete after just a single transaction. So examples like that often include things like swaps and escrow, where you're just trying to send some value to the right person. And once that's sent, it's done, right? That happens right away. And then it's over. And so in that case, you say, okay, well, there's a certain person who's entitled to receive this value under some conditions, and then that's the end. It's sent, and it's withdrawn from the contract. There are escrow mechanisms that are like that, too. There are other cases that are not that way, right? There are other cases where, in fact, some things will exist over a long period of time and require multiple related transactions to occur. So vaults are an example of that, where you intentionally slow down the withdrawal and intentionally make it into a multi-step process. Prediction markets are like that, right? We have an example implementation of a prediction market in Simplicity, where, wow, there are a lot of related transactions, because you have to show up in the prediction market and you say, I want to create a pair of yes and no contracts, and I want to spend money on them and lock that value. And then later on you show up and you say, by the way, an oracle said, I'll talk about oracles in a moment, that this contract resolved to no. Can you please remember that this is a no? Okay, by the way, I have a no token here. I want to get some of the value back, right? There are several different transactions that have to occur at different stages that involve actually potentially many different people, because many people may invest in that market and they may trade those tokens around. And so you might actually have thousands of people who are interacting with the contract on thousands of occasions in different stages of its life, like before the contract is resolved and after it's resolved. Okay, so that's kind of at the opposite extreme compared to a swap or something, compared to a single transfer. And our loan contract is another example, right, where you have different stages that it can be in. Like someone has deposited some money and is looking for a lender. Or later, someone has fulfilled the loan request and actually made the loan. Or later, the loan has been repaid or not repaid, and then the lender wants to liquidate it. So in that case, you've really got to keep track of this history to some extent. You've really got to remember what's going on, what's changing, what's going to happen in the future, who is entitled to what right now, and who would be entitled to something later if this happened, right? If the loan is repaid, if the loan is not repaid in a month from now, then we'll have different transactions that are permissible. Either recover the collateral or liquidate and cede the collateral to the lender, depending on what happens a month from now. So covenants are a pattern that allows a smart contract to control assets across multiple transactions and enforce rules whose scope lasts beyond a single transaction. I also have a kind of abstract diagram of this idea. And that was down here. Okay, right. This is a very abstract representation of a general covenant. So the last will was a really specific example of a specific application. This is an attempt to capture the general idea that there's this contract that has an ongoing existence, and each of these arrows would be a transaction that changes the state of the contract in some way. So one thing that can happen is an asset deposit, where you put assets into the contract, and the contract may be written in such a way that it then remembers that you're entitled to something in exchange for that. So you're not just donating it, but the contract actually knows that it has an obligation to you because you deposited something, right? Like with the prediction market, you can deposit money and then it will be willing to give you in exchange a yes and a no token in exchange for your money. So it's not just like you donated this money to it, but it's like you purchased something from it and it knows that it owes that thing to you. And then you could have a transaction that performs some update where you're changing something or informing the contract that something has occurred. For example, in the prediction market example, the version that Tommy from Resolver wrote, that I'll give you a link to later, lets you inform the contract who won, and then it remembers who won after you tell it. So you give it an oracle statement, and then it updates its state based on the oracle statement to remember, oh, the yes side won, or the no side won, and then it never forgets that afterwards. So in that case, you're not actually moving any money out of it, you're just letting it know, by the way, the no side won. Please remember that. And then there are these other cases that can occur, right? You can have multiple different actions that are allowed. At some point, someone may be allowed to take money out of the contract. At some point, someone who deposited something may be entitled to get a refund. For example, something didn't happen, so you get your money back. Right, that's a common pattern as well. So this is a very general sort of abstract representation of things that a covenant might do. And each of these cases is going to need to have some code in SimplicityHL to say, this is an authorized form of transaction sometimes. And then try to say, when is it authorized? And write down the rules that describe what makes it authorized, right? For the refund, you need to say, when is it that the contract has timed out and you get your money back, right? How do we know it's you? Do you need to make a signature? Do you just send it back to the same address that it came from? Those are both possibilities. That would be expressed in the code. Okay. Moving on to oracles. You know, I want to move on to oracles, but I'm also realizing that I think we've reached the time for the coffee break. Coffee break. Yeah. So let's have the coffee break. We're planning to have the coffee break for 30 minutes. I really appreciate your patience. I know this is a huge amount of information, and I'm kind of throwing it at you rapidly and at some length. So thank you again very much for being here and for your attention, and we'll have the coffee break for half an hour. If people are curious to ask questions during the coffee break, you're welcome to, or if you just want coffee, that's awesome too.
For the adjusted native function, where do I find the implementation of the underlying code?
Oh yeah, the question is, where do you find the implementation of the jets? So the implementation of the jets is in the Simplicity repo. So I'm going to give a link to all of the GitHub repositories for all of these things. Let me show those links and I'll point to which one contains the jet implementations. Yeah. I got some great questions during the coffee break. I don't think I even have time to repeat what all of the great questions were, but they were great. We talked a little bit about the formal verification. I talked to several people about the state management and state commitments and how that works and how to use it. Really fun conversations. So thank you to the people who asked those questions. And we did have one question where I thought that I might have forgotten to constrain the covenant in the third time's the charm so that the money could actually be stolen from it. I went back and checked again, and in fact it's okay, because the state management code is actually enforcing that it's the same program. But there are a lot of subtle details in some of the covenant programming. And I'm sure we'll have occasion to talk more about that, and I'm sure I'll write more documentation about that, because it's a very unusual part of our model compared to a lot of other programming environments, to talk about having to send assets back to yourself and how to check whether they're being sent back to yourself, and all of the details that follow from that. Okay, I want to talk a bit about oracles, which are a big topic, which come up a lot in all blockchain projects, I think. And I'm sure many of you are very aware of the oracle problem, but fundamentally the oracle problem is that the blockchain really talks about itself. It doesn't talk about the outside world. It doesn't talk about the physical world. It talks about the fact that certain bits on the blockchain are related to other bits on the blockchain, such as certain UTXOs have been spent or have not been spent. Certain UTXOs are allowed to be spent or are not allowed to be spent. One block followed another block, right? These are all statements about the blockchain itself. They're not statements about things like what was the weather like in Turin today, or who won this election, or what was the price of wheat in Chicago yesterday, or how bad was the hurricane season, or did this person suffer a loss that the insurance should compensate for, or does this company's database agree that this person is an approved recipient from a list of approved recipients? All of these things are statements about things that exist outside of the blockchain. And so traditionally, representing that information on the chain is known as the oracle problem, and it exists for simplicity development just as it does in other areas of blockchain development, right? Simplicity, as I said, can't make network connections. And so we need the outside world to be described to our contracts through what we call oracle statements, which are basically any form of digitally signed statement that will confirm some fact that a contract needs to know. And that does require trusting someone. So it tends to remove or undermine the trustlessness property of a contract that might otherwise exist, because you're saying this entity is allowed to say that this is true, and the contract will believe what that entity says. So you're introducing trust there. If you have a price oracle, if you say we're going to exchange one currency for another, and the price oracle tells you what the current market price between those currencies is, if that oracle makes a false statement, then one person can really take advantage of that at the expense of another person. So the truthfulness of the oracle statement is in no way technically guaranteed, but it's very important because it could result in one person unfairly gaining or losing compared to another person. Okay, so basically oracle statements, by the way, you can tell that this image was made by an AI because the third leg of the tripod is kind of balancing over the opening rather than being supported on the ground. So the physics here is not quite right, but it's kind of a nice oracle otherwise. Oracle statements basically are digitally signed assertions, which in the simplicity contract are provided to a contract through the witness. So in the witness, in the input to the contract for your transaction, you can say, here is a statement and here is a digital signature for that statement, reflecting something from the outside world that this specific contract cares about confirming. And that digital signature is going to confirm the truth of that statement. Right. Here's still another diagram of this, right? Maybe for a price oracle, you have a statement that a current market price between two currencies is a certain value. You have a digital signature by a certain key belonging to a certain oracle. And then the contract is able to say, well, I was told to trust that key, so I accept that that is in fact the current price for whatever logic I have related to a price about allowing or prohibiting certain transactions when a price is at a certain level. Sorry, I wanted to say also again, this is also a way that you can link an external database into your contract. So if you have a conventional database that contains some kind of fact that your company believes is true, some kind of policy that you want to enforce, we were talking to a couple of people here about things like only allowing certain addresses to transact with a contract and having a list, right? Like these are approved suppliers of a company, or these are the employees of the company, some kind of list that might be in a database, and you want to say, is this in the database or not in the database? Well, you could also make your own oracle where you digitally sign the results of your database queries, and then you can provide the results of those database queries in the witness to your contract, together with the digital signature from your own server. And then it says, okay, the server from the company that wrote this contract has digitally signed a database query result that says that this thing is true, that this is in the database, that this is not in the database, therefore this is allowed or not allowed, for example. Right, so it's a way that you can connect a database. Because the Simplicity program itself is not going to be able to initiate the connection to the database. It has to be told through the witness what's the case, what's not the case, right? I wanted to mention time locks. I have a whole document on time locks. Liquid inherits from Bitcoin a set of time lock mechanisms. There are actually 4 different kinds of time lock. We have some jets related to enforcing these time locks. These are basically saying a certain transaction can only occur after a certain delay. So we can say, well, the last will contract that I showed before is an example of that, where you say you can inherit these assets if the assets haven't moved for 180 days. So if the assets haven't moved for 180 days, is a time lock question. It's a time lock assertion. A lot of vaults that have a delayed withdrawal pattern would use a time lock in some way. It's also, people's rights and responsibilities under a contract might change over time. So we have liquidation of a loan as another use case for time locks. So we might say, well, we have this loan. The term of the loan is 1 month. After 1 month, the loan should be repaid. If it has been repaid, then the borrower can reclaim the collateral immediately upon repaying the loan. If it hasn't been repaid after 1 month, then the lender can liquidate the loan and take the collateral. So that after 1 month is again a use of a time lock. And that actually is expressed that way in the lending contract. That we actually have this specific time after which a certain action can be taken that could not be taken before then, before the loan has reached its maturity period. It's also very desirable in a lot of cases to have a last resort refund pattern. So this would be to say, if the purpose of the contract fails, then after some relatively long amount of time has passed, people can claim their assets back from it. If the thing that the contract was supposed to do just never happened, then rather than having all the money stay in the contract forever, you could say after 6 months, people can claim the assets back to the addresses that they were sent from. That can be very desirable, for example, if you have an event that relies on an oracle. Because if that oracle operator disappears and stops operating the oracle, then a claim that relies on the oracle statement could never occur if the oracle is no longer issuing oracle statements. So in that case, you might want to say, well, if 6 months have passed, or if a year has passed, and whatever relied on the oracle statement hasn't happened and the assets are still inside the contract, people should be able to take them back. Because presumably that means that the oracle is just not operating. So rather than have the money stay there forever, maybe there should be some form of refund, some form of last resort action Right, and again, you can have intentional delays in vaults, which was the first example that I mentioned. Okay. We're getting pretty close to the end of this lecture part. I'm going to have a section, we still have this section, but I think following this, we're going to have a section with an interactive demo for those of you who have laptops, where I'm going to go through some demos using our code space. And if you have a laptop here, you'll be able to follow along and run the demo yourself. I still have to get through this section first, but we're getting close. Right, so I wanted to talk about our developer tooling, and I know for the hackathon this will be especially significant, right, because many of you will try to develop smart contracts and try to develop also code that interacts with them. And this is a really significant piece because not only do you have the smart contract itself in SimplicityHL that describes the logic, but you have some kind of app that interacts with it by building transactions and witnesses and creating a user interface. Because the Simplicity contract itself doesn't have any form of user interface, and it doesn't take any actions on its own. So there must be some form of app outside of the contract that understands the contract well enough to be able to actually interact with it on behalf of a user. That might be a wallet app. It might be a specialized app related to that specific contract. But there needs to be software that understands how to actually make the contract do things. That software is not written in SimplicityHL. It's written in some other language. Our default recommendation is that that language should be Rust. A lot of our tooling is written in Rust. A lot of our low-level libraries are written in Rust. Several of the tools I'm going to mention work with code written in Rust to drive a SimplicityHL contract. However, that's not an absolute requirement. There are other tools, including other tools that I'll mention, that are suitable for developing in other languages. So you'll have some choices here. Okay. So let's talk a little bit about some of these things. Right. So we have a set of tools to interact with contracts on the command line. These are often very useful educationally for experimenting with SimplicityHL, for learning about it, for debugging things, for testing your contracts. These are not really aimed at building any form of end-user application. So these are essentially developer tools and educational tools and testing tools. For a lot of us working on various aspects of Simplicity, these are still things that we use quite a lot. In fact, the demo that I showed you so far and most of the demos that I'm going to show you are using these tools. Right, so we're running command line tools, and the command line tools are compiling contracts, and then they're performing various other tasks with HAL Simplicity. So we're calculating the contract's address, possibly when combined with a state commitment. We're building a transaction to claim assets. We're looking up other data related to a transaction. So these tools are called SimC for the SimplicityHL compiler and HAL Simplicity. And those are, again, command line tools. And most of the demos that I have for you here are actually based on those tools. But if you try to make an application with them, it's basically going to be like a bash script. So it's not the friendliest environment in which to develop an end-user application, like for creating a user interface. Okay, so for building apps around contracts that provide a user interface and that are able to let users actually do something with the contract, our main tools at present are Simplex and LWK. And you heard a bit about LWK in the morning from Pablo. Basically, these tools are providing higher level SDKs that applications can use to interact with SimplicityHL contracts. And again, that primarily means creating transactions and creating witnesses that ask the contract to transfer value somewhere. It also includes some other surrounding functionality. For example, it could include looking up blockchain data to find out what contracts exist, to find out the state of contracts that exist. So I'm going to talk a little bit about Simplex and a little bit about LWK, And I'm going to very quickly show you examples related to them. Let me see how my code space is doing. Well, let me come back to the Simplex demo, but let me talk about what Simplex is, right? So Simplex is an orchestration tool. It's aiming to be kind of similar to Cargo for Rust or to Go for Golang. So basically a tool like for project management that does dependency management, that handles testing, that handles some aspects of project configuration, that can handle some aspects of generating boilerplate code. So this is kind of an all-around orchestration tool, specifically meant for developing applications in Rust that interact with SimplicityHL contracts. Okay, so yeah, it can deal with dependencies. One really helpful feature for Rust developers is that it can analyze your SimplicityHL code and generate some boilerplate Rust code that's specialized to interact with your specific contract. So that's a really nice feature. And it provides a test framework. So you can build tests. And it actually will run those tests locally. It will spin up its own local elements network just on your machine and run the tests locally, which is very fast. And you don't need to publish those tests on the Liquid testnet, which all the other tools that I'm mentioning currently do. Right, so it generates Rust code to build witnesses and transactions. I'm going to show you that, but I want to do that in the code space. So give me a minute because I'm going to open the code space soon. And I'll show you Simplex there. But I'm also going to mention LWK. Right. So LWK is the Liquid Wallet Kit. It's quite a large library and SDK for building apps in general on Liquid. A very nice feature of LWK that Pablo mentioned earlier is that it actually targets a very large number of high-level languages for developers. I think there are currently about a dozen languages that LWK generates bindings for, meaning that you can call into LWK from those different languages. Right, so you can call into it from Rust. It's actually written in Rust. But it also has, for example, Python bindings and JavaScript bindings and other bindings so that you can call into it from other languages. One cool thing that we've seen for a number of projects, and our colleagues have been directly using this, you can actually compile to a WebAssembly target. So you can build something with JavaScript with LWK and compile to WebAssembly, and you can make a web application that can interact with Simplicity contracts on the blockchain, which is a nice thing if you like to develop in JavaScript and you want to have web apps as your sort of main recommended way to interact with your contract. The LWK WebAssembly target now facilitates doing that. So you have like a self-contained web application generating transactions in response to actions that the user takes. And LWK does a lot more than this. And the simplicity features in LWK are very recent, and they're currently considered to be alpha quality. But they do exist. I wanted to show you. I think I can do this locally. Okay. Have to keep making these bigger. Oh, great. Yeah. Okay, I did actually have a copy of the LWK checked out, which is good. So in the current LWK repository, you can run just Python build binding simplicity. And it's going to create the Python bindings for the portion of the simplicity support that exists in LWK. So I'm actually going to be able to show you a Python program that will interact on-chain with a contract. So let me do that. Okay. So this is a pay-to-public key script. We'll see this. Right. The output of this may not be very exciting. We're basically spending a simplicity pay-to-public key contract, which is about the simplest meaningful form of contract that exists. Very similar to pay-to-public key natively in Bitcoin script, which is possibly the simplest non-trivial form of Bitcoin script that exists. Right, so this just worked. May not have been very clear what it was doing from the output, but it was basically taking all of the steps that were required to spend a pay-to-public key simplicity contract from Python. And I'll just quickly show you the Python code. Okay. So the concepts here actually would be about the same using LWK from any high-level language. I did not write most of this Python code. Most of this was written by my colleague Kirilo Ryabov, who also is the main author of the Simplicity LWK integration itself. And so he wrote some Python tests for that. What I've done here is modify that and extend that in such a way that it interacts directly with Liquid testnet, because his examples weren't actually live on Liquid testnet, and this example is. But still using Kirilo's LWK simplicity. So you can see this looks like Python, right? There are quite a number of steps that are involved, but they're all represented here as fairly high-level concepts that are fairly related to what you're trying to accomplish with the on-chain transaction. And the actual LWK API calls here would conceptually essentially be the same no matter what language you were programming in. So if you wrote this program in JavaScript, you would basically be making the same function calls into LWK in the same sequence in order to accomplish this. Or if you wrote it in one of the other languages that LWK has bindings for, you would basically be doing the same. Okay. Anyway, if you're interested in development with Python, I have put this in the code space, which I'm going to be sharing with you, so you'll be able to look up this program and see it as an example of how you can interact with simplicity contracts from Python. Right, I don't want to attempt to explain what each of these things is right now because it would be pretty time consuming. Each of the methods of building transactions is pretty detailed and involves a lot of steps. So you can build them from Rust, you can build them on the command line with HAL Simplicity, you can build them in a variety of languages with LWK, you can have Simplex generate code to help you build them from Rust. In each case, there is still going to be a number of steps involved in creating the actual blockchain transaction. But in each case, you can look at a worked out example to imitate that example. Let me actually, while I have this open, let me actually just show you something from Simplex. Okay, so this is a Simplex configuration file. It's in TOML format. It lets you set up a whole project. Again, assuming that you're doing your development in Rust, it's going to help you structure that and it's going to help you generate it. And I'll just show you the simplex build command because the simplex test command has a problem on my local machine. If I run it again in the code space, it will work. Okay, I just ran simplex build. Again, this is just one of several functionalities of simplex. But let me show you what simplex build created for us. Okay, so this is some Rust code that is basically boilerplate code related to building transactions for this specific contract. And this was all auto-generated by Simplex. So again, Simplex does other stuff, but this is kind of the first feature and the, I don't know if I should say main feature. It's one of the most appealing features and one of the coolest features of Simplex. That all of this Rust code was written for us automatically by analyzing the SimplicityHL contract. And it looked at what that particular contract is expecting, and it wrote all of these Rust functions that directly help you make a Rust program that generates transactions that can spend from that particular contract and create a witness that that particular contract will accept. And so this is, for Rust developers, potentially a real time saver because you can see there's already a lot of detail here. This was all auto-generated for you. So you're at least getting this kind of high-level abstraction auto-generated in Rust for your simplicity contract. So that was simplex build, right? Just to return to talking about what simplex is, that was the slide again. Okay. Yeah. So I just want to recap that because I know I just threw a lot of details at you and I just want to sum it up. In some way, if you're making an application based on simplicity, you're going to want to write a smart contract in SimplicityHL, and you're going to need to write some kind of app or some kind of library or some kind of tool that actually then interacts with that contract. That's very likely to be specific to that contract in terms of what it does and what it expects and how it's used. And so we're working on a variety of tools to help you accomplish that. So the low-level library is called Rust Simplicity. The code that Simplex generated is actually using Rust Simplicity as a dependency to actually make the transaction, right? So Simplex generated this Rust boilerplate that uses Rust Simplicity to do the transaction building. We also have this command line toolchain, which is SimC, the compiler, and HAL Simplicity to make these transactions on your command line. And we also have LWK, the Liquid Wallet Kit, which lets you do development in other high-level languages that are not Rust. It doesn't have the same code auto-generation feature. And so these are some choices that you have right now, at least for your projects that you may be working on tomorrow. I'm happy to talk more about these. I'm happy to show more about how to use them. I want to do the simplex test demo when I open the code space, right? Okay. This is the final section before the interactive part. So basically, I'm just going to review what the various web resources are that we have available related to simplicity. I'm going to show a bunch of QR codes. You don't have to scan them if you don't want to. I'm going to also send all of them to the Telegram group. So feel free to just hear what these are and receive them on Telegram instead of scanning the QR codes. But if you'd like, you can also scan one or more QR codes. Okay. I'm going to come back to the use cases page, right? This is the Simplicity Community Telegram group. This is different from the Bootcamp Telegram group. The Bootcamp Telegram group is specifically for this event here today and tomorrow. This is the general Simplicity Telegram group where you can keep up on news about Simplicity, you can ask your questions, you can share your work and your projects with the entire Simplicity adopter community. Okay? This is the Simplicity developer documentation. I've been the main person writing that documentation. I'd be very grateful for people's feedback on that documentation, what you found helpful, what you found confusing, what you would rephrase, whether there's other documentation you'd like to see. I'm certainly aware that there's a lot more documentation that I need to create, but we've put a fair amount up about jets, about covenants, about the UTXO model, language reference, differences from Rust, differences from EVM and Solidity. So there's quite a lot of material. So please do check that out. This is the Simplicity code space. In the next section, I am very soon going to encourage you to open the Simplicity code space, and then we'll be able to do a few examples together. You can also choose to use the Simplicity code space for your own development work. There are certainly other ways to install these tools. This is not the only option. The reason that I favor this right now for our interactive demo is that it's relatively standardized. So it's pretty likely that everyone who uses the code space will get access to the same environment. So you should be able to complete the various demos in the code space in the same way without having something unusual or awkward happen related to your individual system. This may be more useful tomorrow, but I'm going to have to regenerate it. But Blockstream operates an API with an instance of a tool that we created called Esplora. This is a blockchain data API where you can look up information about transactions. This is a link to an API key which will give you non-rate limited access to Esplora today. So it's going to expire tonight, and I'm going to generate a new one, and I'll give you the new one tomorrow. Basically, Esplora is available for free, but it does have rate limits, and particularly because we're all connecting from the same IP address, I was concerned that if you build projects that look up blockchain data in Esplora, you're likely to get rate limited if other people are also running projects that do the same on the same network. So I did arrange with the Esplora developers to get us this non-rate limited key. And again, another one for tomorrow, which I will share tomorrow. So if you want to use that method to obtain blockchain transaction data while you're here at the hackathon, that's an option. There are other ways to get that data, right? Esplora is not the only option. But LWK, for example, has a whole set of functions to let you download transaction data. So a lot of the demos that I've been doing here actually need to look up the prior transaction that you're trying to spend, or actually need to find out when a transaction has been published. And in some cases, you might do that kind of thing via an Esplora query. And if we're all doing it at the same time, we may have these rate limit troubles. Okay. This is a list of all of our open source projects related to Simplicity on GitHub. There are now about a dozen of them. Again, I'll share this also in the Telegram group. Right, so this is basically all of the source code to everything that you're seeing here, and all of the developer tools that I mentioned. Okay, great. So that's the end of the lecture part, and we're going to move on to the interactive demo part, which is the final thing that I have programmed. Right. So I mentioned this code space. Code spaces were actually new to me. I don't know how many of you have made use of code spaces. Code spaces are a feature that GitHub and VS Code provide to use a format that's not GitHub specific called dev containers. This is a standardized format for a Docker container to be used in connection with software development. And so basically you can open the code space with various tools, and you get your own relatively standardized instance of a certain development environment in which you can perform certain tasks. So this one is related to simplicity. And we're going to open this up. Basically, the two easiest ways to open this are if you have VS Code, you can clone this and then open that repository, and it will say, do you want to open this in a container? And if you say yes, then you get that whole environment. Or if you're logged in on GitHub, you can open it in your browser. Basically, if you open it in your browser, my understanding is that GitHub itself will create a virtual machine, and it will let you talk to that virtual machine that's running a copy of that container. So it feels like you're opening it in your browser. I guess you're actually opening it on GitHub's server, right? But either of these should work. I'm going to go and I'm going to open this in my browser here. And you can see that process if you're not familiar with it or if you haven't done it yet. Just to show you where this user interface feature is, this is only if you're logged in on GitHub. Right. So you might be accustomed to this part where it tells you how to clone it, but there's actually another tab here called Code Spaces. And you can click on plus to create a new code space based on that repository. I actually have one that I opened earlier today. It gives them humorous names that are meant to be memorable. So I think this one is called Psychic Space Giggle. I think it tries to make them funny so that you'll supposedly remember them. Right. So it's now connecting here. Okay. Yeah, so we have various things here. We have things related to Simplex. I didn't actually manage to get a full copy of LWK in the code space yet, which means if you want to try the LWK example here, you'll actually need to clone the LWK repository yourself. I'm sorry about that. I can possibly change that tomorrow. But I think the other examples will work directly as is. So we can go through each of these. Again, you're welcome to just try these yourselves, but I'm going to try them one by one, and I'll talk a little bit about what each one is and what it's doing. I try to show you a little bit of it. Okay? But hopefully many or most of you have this open on your own machines in some way. Okay, wow, that's pretty big. That's not too bad. Right. So this is inside the Docker container, derived from this dev container. And we have just a few things here to show off different ways of interacting with and developing for Simplicity contracts. So the exercises versions, right? We have 4 of them right now. Just to review what these are, this one is a pay-to-public key contract, something that you may be very familiar with from Bitcoin. We're just replicating it in SimplicityHL to show more about how SimplicityHL works. So that's certainly something you could do and probably frequently do if you ever send people Bitcoin with traditional Bitcoin software. You probably use a method similar to that. This is pay to multi-sig. Again, also something that can be done with traditional Bitcoin script. But the code in SimplicityHL is pretty readable and pretty extensible, I think. So it starts to be nice in terms of understanding what it's doing and how to change it. This one is the third time's the charm that I showed you before. Now you can try it for yourself and we can look a little bit more at how it works. And then this one is called a hash time lock contract, HTLC, which is a cool mechanism, conceptually very simple, which is used in some forms of swaps, like cross-chain asset swaps. And we have a SimplicityHL implementation of that. Okay? So I'm just going to go through each of these and I'll show you the SimplicityHL code. I can show you the shell script and we can run the shell script. Basically, each of these is going to make a live Liquid testnet transaction that you'll also be able to see in the Explorer. So you'll be able to see what the on-chain transaction looks like when you interact with these contracts. We might run into some API rate limit issues because if several of us are doing it, I'm not actually sure if you're using the same code space on GitHub, if there's a small pool of IP addresses that outbound requests originate from, or if each one gets its own IP address, right? So if you have it cloned locally and you have it in VS Code, it's going to come from the Wi-Fi here, and then we might get rate limit issues. If you have it remotely on GitHub, maybe there's enough diversity in the IP addresses that we won't have rate limit problems, but we'll see. And that could apply to the faucet because we're requesting test coins for each contract to be stored in the contract before they're claimed back from the contract. Could also apply in some cases when we use the APIs to look up the transactions, but we'll see. Okay, so this is the pay to public key contract. This is in SimplicityHL. This is in the SimplicityHL examples. If you clone the SimplicityHL repository, there are a couple dozen example contracts. This is one of the ones that's present there. And this is pretty short. It's condensed this into one line. It might be more readable if we broke it out into multiple lines. But basically here we're saying this is a public key. This public key is actually the public key in the Schnorr signatures that corresponds to the private key 1. We saw that before in another example. So if your private key is the number 1, then this will be your public key. Okay? And the idea here is, as it says, the coins move if the person with the given public key signs the transaction. So a very basic mechanism. But here we're verifying it with a couple of jets. So we're using this jet to verify the signature. Sig all hash is generating a sig hash for the entire transaction. The sig hash is the value that should be signed. And in this case, it represents a summary of basically everything about the transaction. You can also choose to sign less information than that if there are some things that you don't want to constrain by the signature. And we're looking for the signature to be provided in a witness. Okay? And we can run here bash demo.sh, and it's going to output a lot of details about the transaction that it's building. And we're going to actually build the transaction and send it to Liquid testnet. So the first step is to fund the contract by requesting assets from the faucet. Okay. Well, so we're going to compile the program. Right, so you saw the source code in SimplicityHL. So this is the low-level simplicity version of the compiled program. I'm happy to talk to people more about the low-level simplicity, but we're not really attempting to teach it or teach much about it right now because we don't expect that most developers will make very much use of the details. It is quite a substantive project with a lot of innovation that went into it, and we have a lot of interesting technical documentation about it. But again, I'm not really trying to teach it here today. But this is the compiled representation. We can get like a disassembled version if you want to see some of the internal logic of that, right? But this is making, actually, this is essentially the disassembled version. So that's a representation of the low-level simplicity that corresponds to the SimplicityHL code, right? The other thing is that we get a specific liquid testnet address representing that specific contract. So if you send coins to that specific address, they're controlled by that specific contract, right? And you saw that we hard-coded a specific public key that's entitled to spend this asset. What would happen if it were a different public key? We would need a different private key to spend it. How would Simplicity know that we should use a different private key? Yeah. So in the code, it's verifying against a specific key. So if that key is different, then the signature won't match. How does the Liquid blockchain consensus know which version of the contract to use for a particular transaction or a particular asset? Perfect. This address is going to be completely different depending on every aspect of the source code, including the public key. So if we change the public key, this is going to be a different address. That's exactly right. And so when we send the coins to a particular address, we're committing to all of the logic associated with that. Whatever source code was there, that's the code that controls that asset. Okay, great. So yeah, we have this contract address, right? We're going to ask the faucet to send us some coins. Okay, the faucet sent us some coins to that contract. That's great. Okay, now we have quite an involved process where we build the transaction. I have a number of demos here, so I'm not planning to talk about what each step is, but you can see in the bash script each step with HAL simplicity that's involved in building this. And I have some comments in the script that talk about what each step is doing. So if you're interested in learning to build these with HAL simplicity, you can imitate that script or read the comments and find out what the step-by-step details are. But basically we are building, a transaction, and having created a form of the transaction, we know that we need a signature. And we were able to ask what the sig hash should be, that is, what value should be signed to approve this transaction. Knowing that and knowing the private key 1, we were able to generate a signature. There's a little subtlety that the digital signature method here has a random nonce in every signature, which means every time you run the sign command, you get a different signature. All of them are valid, but no two of them are identical. So here I ran the command just to show what the output looks like, and I got one signature. Here I ran the command again to capture that value in a variable, and I got a different signature, and that's because the digital signature there is non-deterministic. But each value is valid, right? There's a very large number of valid signatures. Okay, so now we create this witness file that includes the signature as a way of providing that to the contract. So we're saying, hey, we're trying to spend this. Here's the signature that proves that we're allowed to spend it. And again, the witness is the way that we pass that input to the contract. Okay. The SimC compiler can accept the source code and the witness. These two are going to be combined in the transaction. So we're building the transaction. We're saying from this UTXO to this address, we're spending using this contract, and here's the witness that should be passed as input. That's enough information for a node to run the program and see if it approves the transaction or not. Hopefully it will approve it. Okay. That's the transaction that's ready to go on the blockchain. And it went on the blockchain. Okay. So we get at the bottom here a URL if we want to look at the details of the transaction. This should be able to open in a new tab, right? Here it comes. Great. I set this to Italian before. Not every single field is translated, but some of them are. Maybe we should file a bug to translate the rest of the fields. Okay, it's not confirmed yet. There's a transaction fee. Okay. Quite a mix of translated and untranslated field names, I guess. Right. So all of that data actually went on the blockchain as part of our transaction. All of the details about the program that we were spending, what witness we passed to it, what UTXO we wanted to spend, right? And we sent it to a certain address, and that's the output 0. Okay. Anyway, there's a lot of technical information here about the transaction. If you want to learn more about Liquid transactions and Simplicity transactions, quite a lot of the details are here, right? Going to go back over to the code space. I am tempted to move on to the second demo, but I'm wondering if anyone has any questions about this one. Maybe I'll just move along to the second demo. Okay, so this is, so actually here, some of this scrolled off of the screen, right? This is a much longer contract. It does a lot more. Okay. This is exercise number 2 in the code space. This is called P2MS for pay to multisig. Right, so pay to multisig is also a common pattern in Bitcoin and Bitcoin-like systems. We're saying there's a certain number of keys, and we're saying there's a threshold, a number of those keys that need to agree in order for a transaction to occur. And this is a useful security mechanism if you want to spread trust around. For example, if you want to create some kind of backup mechanism and say, well, I'm going to give backup keys to some people, but we need several of them to agree in order to use the backup so that one person can't use it unilaterally. Or if you wanted to distribute control inside of a company, right, you could say, we'll require the agreement of several executives of the company in order to perform this transaction, in order to send these assets. Okay, so it's a common pattern. So we defined several functions here. We are working on a standard library. The not function is something that's going to be defined in the standard library, at which point you won't have to define not in your programs. But here is a definition of not in SimplicityHL for Boolean not. Here's a function to check a signature, right? It basically is just calling that same jet that we saw before to check an individual signature. And the thing about this jet is that if the signature is invalid, then the program will actually reject the transaction. So if you're calling this jet and the signature is not valid, the program says no to the transaction. And the default, if you get to the end of the program without failing an assert, is that it says yes to the program, to the transaction. Yeah.
When you talk about an invalid signature, here it doesn't mean that the private and public match, but just that the SIG is a valid SIG and does determine length and determine parameters.
Yeah, we don't technically compare the public and private keys because we don't see the private key at all. So we're really just following a signature verification algorithm for something that is claimed to be a signature from a certain key. Sure. Yeah.
Because I would expect that when I sign something and not to check if my signature is if I'm authorized to do that signature, I would expect that that part was handled in the line with a check sig case or not.
I'm not quite sure that I understood.
So inside that draft, there is already the verification that I am authorized to do that signature that I provided.
Oh, so the trusted keys here are listed later on in the program. So when we call checksig, we're providing a specific public key as an argument. So these are the specific authorized keys for this particular contract. And the checksig takes that as an argument. So, yeah. So it says specify a public key and a signature. And then here it's just saying, well, the message that's signed is the SIG all hash in every case. So then we're attempting to verify that signature as a signature under that key over that message, over that SIG all hash. But the specific trusted keys are listed at the bottom of the program. And then there's this function check2 of 3 multisig, which is doing a slightly annoying thing about counting how many valid signatures there are to make sure that that total is 2, because we have 3 different keys. So we need to check each provided signature and count how many signatures were provided, each of which was valid. Could you overflow the U8? You cannot overflow the U8 because we assert not carry. That's a great question. So yeah, the increment 8 indicates whether there's an overflow of the U8 type, and we assert that there is no such overflow here. And then here, we say that we assert that the counter representing the number of valid signatures is equal to the threshold value, which is 2. And then these again are the trusted signatures. Okay? Trusted public keys. So any 2 of those 3 keys can make signatures that will cause this transaction to succeed. Okay? So here we have these 3 private keys. And we have that contract. Right? And we again compile it and we derive an on-chain address for this contract. We're again going to request the Liquid testnet faucet to send us some coins in that contract. And there now, we can also view this in the Explorer. It's going to be a transaction from the faucet to the contract. So there's an input and an output. Okay. Now we go through these various steps again to create the transaction. Now in this case, we're going to create 2 different signatures. So we're generating a signature by Alice using the private key 1. We're not generating a signature by Bob using the private key 2. And we are generating a signature by Charlie using the private key 3. So we have 2 signatures. And we've put those 2 signatures into the witness using this list of 3 option types. So it's an array of 3 option signatures. That may be somewhat familiar to you if you're a Rust programmer. This is a very Rust-like notation. So the first signature is present with some. The second signature is absent with none. That's Bob's signature, which was not provided. And the third signature is present again with some. That's Charlie's signature. Yeah. So this is a feature called an option type, which is used in a lot of programming languages if you want to explicitly say that some kind of data might be provided or might not be provided. And both cases are potentially valid. And so in this case, it's defined as option signature. And so for each one, it can either be provided, in which case it's expressed with some and the actual value, or absent, in which case it's expressed with none. And SimplicityHL supports this in a variety of ways so that you can then ask, was that value provided, was it not provided? Yep. Yeah, the question was whether the order matters, and it does because they correspond to particular keys. So it matters that this key was made by, this signature was made by Alice, and that one was made by Charlie.
Do you see this as a limit or a security?
Yeah, the question is this a limitation or is this something useful for security? And I think that it's something useful for security. Some of the reasons for that are a little bit complicated and relate to this issue called transaction mutability, which is to say, for many forms of simplicity transaction and liquid transaction in general, we would like there to be a unique representation for each transaction, which sometimes prevents certain kinds of griefing attacks, where a transaction is replaced by a different transaction before it's confirmed. So if there's only one representation that works, it can actually be more secure because it prevents someone else who sees the unconfirmed transaction from creating a different version that is also valid. I had some trouble with that. I had a whole kind of debate about that with actually some of the people who made this, and I said, like, wouldn't it be better if it were more flexible? And they said, maybe not, because if someone else can change this and make a different witness, that may actually be undesirable if the different witness is also valid. In this case, it's a little hard to see how someone could cause harm with that. But there are other situations where the ability to make a different witness that also constitutes a valid transaction can cause some problems. At least it may be able to cause like a delay in the final approval of the transaction. Anyway, we can also definitely talk more about that. But there actually turn out to be some advantages to having a sort of inflexible structure for the witness. Even though that might seem annoying, it may actually be preferable. Okay, great. So we attached that witness to the transaction, and this is the resulting transaction that's going on the blockchain. And it also succeeded. So because we had 2 of the signatures, we were able to spend from the contract and transfer the assets out of the contract. Any questions about that? Okay, now this is quite a long contract, and you may recognize this because it's the very first one that I demonstrated at the very beginning of the session today. Okay. This was the third times the charm covenant, where you have to ask it 3 times in order to get the assets out. I'm happy to look through this a little bit and talk a little bit about how it works. This particularly illustrates this state commitment mechanism, which you can use to make an updatable remembered state in your contract, where you can then make a transaction that changes that state in some way, which is exactly what we do here. There's a lot of comments at the beginning that talk a bit about how that works. The connection to Taproot for the for the state commitment. I think this is a good way to put it, that as a result of the assertions that we make about certain hashes here, the assertion proves that the UTXO is locked not just by the code, but specifically by this instance of the state data. So you saw before when we had state 0, 1, and 2, each of those generated a different address. And we'll see that again when we run this. But that's this idea, that the UTXO is locked both by this specific code and by this specific state value. So the assets move from one address to another address to another address, and each address includes a commitment, cryptographically, that the state value for that copy of the contract is a certain number. When that number changes, the address also changes. So the assets are moving from this address to that address to that address to that address. This address is committing to state 0. This address is committing to state 1, this address to state 2, and then this one spends the assets and they leave the contract. Okay. So we really have an unlimited number of potential instances of the contract, each one asserting some history or some state value. And then the question is, where should the assets go? They should go to the instance of the contract that makes the correct claim about the history.
Sorry, I have a question about this.
Please.
Because in this example, the number of future states is already known at the beginning of deployment of the contract. What happens if the number of states is not defined at the beginning?
Yeah, so the question was, in this case, we have a very predetermined list of states, right? The state here should be either 0, 1, or 2. Those are the only intended possibilities. The question was, what if it's not defined at the beginning? And in fact, it is suggested, and there's a comment somewhere further in this program, that a best practice is to take a cryptographic hash in some way of all of the variables that you want to be part of the state commitment. So here we have just one variable, which is how many times did we request, right? We requested 0 times, 1 time, or 2 times. A real practical contract might need to remember several things, not just one integer. So the recommended method involves taking a SHA-256 hash of some combination or a list or Merkle tree of all of the variables whose values you want to remember. And in that case, of course, the update is not simply increment by 1. The update would be recalculate the SHA-256 after changing whatever variables need to change. So we might have 6 variables where the state commitment represents all of them by taking the SHA-256 hash of a list of 6 variables. SHA-256 of A, B, C, D, E, F. And then if we change D and F, then when we calculate SHA-256 of A, B, C, D, E, F, the hash will change because we changed 2 variables. And then we store that hash value as the state. So essentially, the state doesn't have to represent a particular state on a list of states, like 1, 2, 3. It could. But more generally, you can have any combination of variables that you want to remember before the transaction and after the transaction.
Okay, but that means that, I mean, okay, all the contract addresses are not predetermined.
Yeah, that's correct.
And the
That's
other
correct.
is then to call this contract again on a new instance, I need to know all the previous state and pass the previous state again, and then the previous state can be verified via the hash.
That is correct. Let me repeat that. That's a very good point. And that does mean more responsibility for the wallet software or for the software that drives the contract. So one point is we would not be able to pre-calculate all of the addresses in that case, which is completely correct. We would probably calculate them as they are used. I happened to be able to calculate them in advance here because they were 0, 1, 2. Those are the only possibilities, so we can see what they will be. But indeed, if we have 6 variables and each one can be an amount of money, and they can all change, and then we hash them, we're not going to be able to predict in advance what all of the possible combinations are. So we would not know all of the addresses of the future versions of the contract in advance. Additionally, as you said, and this is a very good point, the wallet software or the application that creates the transaction must provide the old state to the contract. It must remind it what the state was, and then the contract uses, here we call it load, to confirm that what it was told is true. That may also feel kind of counterintuitive, so it's good to say it explicitly. That because we don't have some kind of database on the blockchain, the actual values are not stored on the blockchain. Only a hash that lets you recognize the values when you see them again, that's what's stored on the blockchain. And so, indeed, the witness must include, I want to say all of the state. If you use the Merkle tree strategy, this is not necessarily true, because one feature of a Merkle tree is that you only need to reveal part of it. Often you only need to reveal the part that you use or that you update, and you don't need to reveal the other part. So it's not quite true that we need to provide everything in the witness if we use a Merkle tree. But we need to provide all of the relevant state that the contract will use in the witness so that the contract can be reminded of it and then confirm it with this load function.
Sorry, one more question. So
Please.
I get that basically with a contract I define the protocol of it, and is there some, and I can generate the UI or the application that interacts with it, that's fine, but is there some want to create some spend conditions for an asset, and then I have to tell the wallet software how to provide the witness and all this stuff.
Yeah. So this is also a really excellent question. This question is basically about wallet integration. I actually had a slide that I deleted that basically refers to the need to solve that problem and describes how we are doing some work on that right now, but we don't have a recommendation yet. But the issue is, suppose you have some existing software that interacts with Liquid, such as wallet applications. One way of putting it is, how would you teach them how to usefully interact with a certain contract? If the contract is new, the existing wallet software would not automatically know how to make that contract do things. Or if the user using the wallet software is able to claim something from that contract, the wallet software would not necessarily know how to make the claim. For example, in the last will example, we have a certain key that is able to inherit the money if the creator dies. Which means if that key is your key, then you're able to claim that. But your wallet software wouldn't automatically know that you're able to claim that or how to do it. So it would be useful if the wallet software could be told, oh, this is the last will contract. If you see that on the blockchain, you can build a transaction of this kind with your existing key and claim that money. So we have a great need to create standards for this, and some of our colleagues at Blockstream are actively researching specifications for that. I think it remains to be defined how general that will be, because you could imagine some contracts where you really ultimately probably need custom software to interact with that contract, because the interaction is so complex or requires so much specific user interface that you would probably not use generic wallet software. But in other cases, we very much want to have a way to load, for example, a JSON file into existing wallets and say, this is a kind of contract. You should know about it. Once you know about it, you can recognize it and interact with it in this way. Part of that is called a wallet ABI. That's a term that's commonly used also in the EVM world. Simplex is working on generating those, but again, the specification is not quite complete. I'm sorry? It's not working on it.
Yeah, they are. It's not going to be anytime soon.
Okay. I'm sorry. That's right. So, I mean, I should say that the Simplex developers are thinking about this as a Simplex feature, but there needs to be a specification for it before it could be written.
And the specification,
Okay. I know that you've been engaged in this conversation actually more substantively than I have, so your comments will be very helpful. But let me give you the microphone. Okay, I'll say one thing afterwards, but you've been really engaged in this.
So a lot of things related to the EVM world are things that we are trying to build similar functionalities within Simplicity, to basically bring people into Simplicity that are used to working in the EVM world, like Wallet ABI and things like that. Ideally, that should be something that we'd be interested in building, and right now we are analyzing what it could look like if we were to implement that. That doesn't mean that we will. We are analyzing it mostly from the security perspective, and if we do end up doing something like that, it's going to be because we are sure that the security implications are within the parameters that we want. We didn't build a whole new language being not Turing complete on purpose to make it secure, to then screw it up by connecting a wallet that in a way that is insecure. So you build the whole foundation correctly, and then you screw it up on the top layers. So Seth is right. It's something that is being analyzed and considered, but it's not something that is being built right now until we are secure or safe enough about the security considerations of everything. Yeah.
That would work like VS Code extensions, maybe a little more containerized. I mean,
there is no. So think about it this way. It all goes back to the hardware wallet. If the hardware wallet doesn't know what it's signing, and there's no way for the hardware wallet to validate what it's signing, it's extremely easy for someone to attack the site or to create a fake site to create a transaction, and then you look at it and say, yep, sign it, and then your money's gone.
Yeah, I was thinking maybe in a mobile environment where I have a basic platform that exposes on maybe API, and I just integrate an extension, and I integrate the paradigm would be one extension for one type of asset, and that extension has visibility to only that type of asset.
All that you want, but until the hardware wallet allows you to validate exactly what's happening, or it gives, or you can get from the hardware wallet exactly the type of information that you need in order to validate by a third party that what you're signing is actually what you think you're signing. It's that process is if you don't do it that way, it's called blind signing, right? That's why I don't like the block, the small device that you basically touch with your thumb and it signs the transaction. The reason I don't like that is because you don't know what you're saying yes to. If the device that is talking to you is compromised, you are signing whatever you ask without any validation.
But you're looking this, so you're looking this problem, and you're trying to resolve it directly on the hardware wallet. Well, I think a normal person should first.
I'm not normal.
No, the normal user should be expected to at least open, I don't know, an app on the phone, verify everything, and then sign connecting the hardware wallet.
Yeah, exactly. But if the connection between the wallet and who is asking the wallet to verify, or who is asking for the transaction to be signed by the hardware wallet is compromised, and the user has no way of validating that the whole flow is correct, then anything can happen. It's the hack that happened a couple of years ago with Bybit.
It was on Ethereum, the famous case of an exchange where exactly this happened, and a lot of money was gone.
$1.4 billion.
And it was even a multi-sig, and the attacker were able to control or inject a false or a different transaction into the signing process. So the people signed the attacker's transaction, and yeah, this is a real problem.
And I assume he talked about JSON files to instruct this, let's say, base wallet to
Yeah.
do more things. I was assuming that you would have used Simplicity. And since you're using Simplicity and you already have built some sort of deterministic checks, maybe you could, I don't know, verify the code automatically. I know that you can't distinguish from a malicious code from benevolent code, but you could warn the user to at least say, please look at the code.
Absolutely. There are a lot of things that can be done, but people get complacent over time.
Yeah.
If you get the same message box with a warning every time you do something, if you change the text, nobody's going to read it. So, and from the design perspective of the security around the protocol, you cannot assume that people are going to be capable of doing something like this. My target when we prepare for security is not you, it's not me, it's my dad.
Yeah.
Right? So I can't even explain to my dad what simplicity is. What I can explain to him is that he's entering into a contract that was validated, and that the 4 numbers in the beginning and the 4 numbers in the end is match whatever he's expecting to see. Right? So we are not the norm in any of this, and you might be building this, and it's okay for yourself, and it's great, and basically it works. But when you're trying to prepare a protocol to work for regular users, there's a lot more checks that need to happen, and then you need to prepare yourself to adapt the process for those checks to be there. Right? So basically, going back to Wallet Connect and Wallet ABI, yes, those are things that we are analyzing, things that we think that if we manage to do them correctly, could bring a lot of users to the Liquid ecosystem, but that in order for that to happen, we need to convince ourselves that we can do it in a way that protects the users from malicious attacks.
But if you couldn't, let's assume, you wouldn't build this, or you would build as a side project, maybe a different wallet from the main.
I'm going to tell you the same I told other people. If this comes out, it's going to come out of my team. If we don't come up with the security level that we are comfortable with, it's not going to come out of my team. right? I'm not going to say that nobody else is going to do it. Maybe other people want to do it. Maybe even other people related to Blockstream. I don't know. But until we are comfortable with the decisions, it's not going to come out of my team.
So I appreciate this because you've been close to this discussion and obviously close to the expression of the security issues. I do think conceptually it's a challenging problem, yes. Right? Because of the fact that anyone can make a contract, and the contract then compiles and you have an address, and the question is, should you sign a transaction with this address? And it's further removed from, we already do have some scams in Bitcoin and everything, where someone can try to trick you into sending money to someone you didn't want to. But there we have some concept of like one person versus another person. And we have the concept of, well, you have to tell me your address, and I have to talk to you and get your real address. That's a little easier to understand compared to some of these issues about what is the effect of interacting with this contract as opposed to that contract, if you don't have a sort of inherent conceptual idea of why one contract is good and one contract is bad, or what one contract does and what another contract does.
Exactly. I think that goes to a different layer of a problem, right? I think the separation is, can you separate a good contract from a bad contract? And that's usually simpler to answer because every smart contract has an audit, right? We can say that Blockstream has audited this contract, or we can say that a third party has audited this contract. And for a regular user, having the check mark from someone who has audited the contract, it's good enough to say that they are willing to trust that the company did their work. The second layer, which is more the one that I was mostly discussing, is now that you know that the contract that you're supposed to be in, you can trust it, then you need to know that you're actually signing as a part of that contract and not another. So that's the second layer.
And potentially every detail can be security sensitive because, for example, in the lending contract, we can confirm that the lending contract was written by Blockstream. But one step in the lending contract is that you propose terms of the loan as the borrower. Yeah. And you propose an amount of interest that you are expected to pay, right? So understanding the amount of interest that you're expected to pay is security sensitive, because if you fail to pay the interest, the lender can seize your collateral. So if someone tricked you into offering a loan with extremely financially unfavorable terms, even through a secure contract that Blockstream wrote and audited, you would still be very disadvantaged. You said, oh, I want to borrow $10,000 and I'm willing to pay 1,000,000% interest per day. Right, and if I fail to pay 1,000,000% interest per day, my Bitcoin collateral can be seized. So even the sort of meaning of the user interface details is security sensitive in that sense, not just the contract being correctly written.
Exactly. So the contract itself is one thing, but in the case, exactly what it says is defining, the contract is basically like a template, right? Then you have to apply the parameters to make sure that the template plus the parameters matches exactly what you want. And if we are all people who are used to this world and understand even conceptually what we are discussing, and it's hard to understand all the implications, when you put that in the normal end user, like I always use my dad as a point of reference because he's a smart guy, but he's not from this world, right? So there's a lot of things that can be attacked by a malicious actor, that can be used as an attack by a malicious actor. So creating the contract and creating everything is the tip of the iceberg, right? Thinking about how to complete the process in a secure way requires participation from everybody, from the people who created the contract, from the people who audited the contract, from the people that basically recreated to make sure that after applying the template, it works exactly the same, that the wallet is in the hardware wallet is exactly the same. There's a lot of steps that you need to be careful with, or that at least you need to have all the information so that even a normal user can understand that this that you had here after applying everything is exactly the same on this side. And they don't need to understand the content. They just need to know that nothing was compromised in the middle.
From my point of view, I see mainly two parts that needs to be audited, or at least ensure that they are bulletproof or scam-proof. And the contract that we could say that maybe as someone validates for you, and then the client you're using for drafting the contract. Because if the contract exposes some parameters, like you were saying, you could borrow something at 1 million% interest. If someone gave you the client, a client-side version that lied to you when is exposing the percentage, the interest percentage. So the focus should be on validating both sides, client side and contract side.
Basically, the thing is, the contract is only the template. And let's say that Blockstream audits the contract. We are not going to validate the parameters of the contract.
No, but if the, sorry.
So I want to finish the demos here. So I think I want to cut this short a little bit. I think that this is a very fundamental discussion that really needs to occur. But I want to just finish this in case there are parts that people want to see, because I think we're 15 minutes away from our official end time. So I'd like to get to the end of these. But I really appreciate the questions and the discussion, because I think there's a lot of subtlety to that, right? And a lot of things about user interface can be security relevant, right? And we can. But so I should say, we have colleagues who are researching how to do this, right? That may be the best thing that we should say. And our colleagues who are researching how to do this are very motivated, and they're thinking very hard about it. And there are, as Pablo says, there are some big questions about, okay, how do you make it meaningful to the end user? I think a default fallback can be, you can have contracts that have a custom app that is the only recommended way to interact with them. And then the trust problems are primarily transferred to trust in that app. However, for many contracts, one might wish to have it be an open protocol and open ecosystem that a wide range of software can interact with. And as Pablo says, this does create some quite interesting questions about how to make sure that the user interface really meaningfully tells people what kind of financial transaction they're interacting with, because the details can become very important and hard to verify and hard to explain in some cases. Okay. And I would love to talk about that more, but let's try to finish some of this because we have officially 15 minutes. But yeah, and I would say for now, as an immediate practical matter, it may be best to think of writing a custom app to work with the contract and transferring the trust questions to that custom app. And obviously, it would be very desirable to find means to not be limited to that, while respecting the kind of security concerns that Pablo has raised. Okay, so we have the details of the state commitment, which have to do with Taproot, which again, maybe I should talk about separately for people who are interested, right? We have a number of steps that happen here. So we do the load and the increment and the store, right? One common pattern that you'll see a lot is that the witness can be used to choose between different actions, right? I alluded to that. This is the way that we typically do that right now. So this witness contains an object called an either data type, also called a sum type. This is one where there are two different kinds of value that can be provided, and the code is able to check which of the two was provided. That's kind of similar to what I mentioned before with the option type, where you could provide something or not provide it, and the code can check which. Here you provide one or the other, and the code can check which. So the two options are always called left and right. And so we use this match statement, and we say if you provided the left object from the either, that, just as a matter of convention here in this contract, represents an update, meaning you're not actually trying to make the final withdrawal. If you provided the right object, as a matter of convention in this contract, that indicates you're making the withdrawal, right? And then these functions actually check that you did it in a valid way. For example, this function checks that the state is actually 2. Both functions check that you made a valid signature with the appropriate key. This function also says, did you send it from an address that corresponds to a state that you said to an address that corresponds to a state that is one larger than that? And it makes a series of assertions. So it says, you told me what state you thought it was. Is that true according to my address? And then you told me where to send it. Is that the same as me, but with the state increased by 1? So there's a whole series of assertions there that happen inside of that update. Okay, so anyway, I wrote most of this contract, so I'm happy to talk about it. If people are interested, you saw it run at the beginning, right? This is basically the same as the demo that I did right at the beginning. Maybe some of the details are a little bit clearer now that we've talked about this in so much detail, right? So we compile the contract now here. So this is interesting. This is the contract with no state commitment at all. This is the contract with a state commitment of the number 0, which is different from no state commitment at all. This is the contract with a state commitment of 1, and this is the contract with a state commitment of 2. Each of those has a completely different address, representing different instances of the contract with different states. Okay? We're getting coins from the faucet. We got coins from the faucet. We're doing the first update, right? Here in the first update, so we make a signature using the private key to approve the first update. And you see we pass in a left signature. That means update as a matter of the convention of this contract. Right? It's an either type, but the specific one that we're providing is left. Okay? Then that transaction happens. Now the state is 1. So we're going to do the second update. Okay. We make a signature with the private key to approve this update. Again, it's a left object indicating we want to do the update action. Question?
The type is either signature, and
Yeah.
not just either signature, because we could pass the two different signatures, one for left and one for right.
The either type always needs to contain 2 types, whether they're the same or different. But it's completely correct that they could be different types, because the kind of data that you need to provide in one action may be different from the kind of data that you need to provide in another action. You could, but then we would lose the distinction between update and withdraw. One way to do it, though, that could work for that, is we could have something called signature and always pass a signature. And we could have something called withdraw address, which could be an option address. And the convention could be, when you're ready to make the final withdrawal, provide a withdrawal address. Before that, do not provide a withdrawal address. And then instead of checking whether it's left or right, we would check whether the withdrawal address is some or none and call the function update if the withdrawal address is none, withdraw if the withdrawal address is some. Is that clear? Cool. We're hoping to actually implement a more automated way to call different functions called entry points. But that's a draft in the compiler right now. It's not completed. Okay, so we're making this transaction, right? This is the second transaction. Now we're doing the third time, which is the withdrawal transaction, right? And here you see we pass the right object. That says we want to do the withdrawal. We're saying it's the third time. The destination address here is an output to the transaction. It's not part of the witness, because the proposed transaction always has a list of inputs and outputs. So you don't necessarily need to give the destination in the witness in most cases, because it's present as an output. Okay. And basically we see that that succeeded, so we were able to withdraw the money. Okay, so that was the third time's the charm. Now with more detail. And we have one more example here, right? This is hash time lock. Now, I actually don't think that anything that I'm going to demonstrate in this demo is new compared to the other contracts. The hash time lock contract itself is a very interesting idea as a trustless mechanism to perform swaps between chains. But we definitely didn't invent that for simplicity. This is just a simplicity implementation of that existing idea. And the branch that I use in this demo is not the time lock branch. So I'm not actually showing how time locks work. So this demo may not actually be that useful to you compared to the other demos, right? It may look kind of the same. So we're providing some coins into the contract, and then we're going to spend them. Right. Okay. This is an example with either the left side and the right side are different types, because the information that needs to be provided is different depending on whether you're performing one action or another action. This one is called complete, and you need to provide a password and a signature. This one is called cancel, and you only need to provide a signature, because the password is only needed for complete. The password is not needed for cancel. So therefore, the left type and the right type are different here. Here we're passing the left type, and so we provide the password, which happens to be all zeros here, and the signature. Okay? And basically it works. So the hash time lock contract is a very interesting construction because of the clever way that it achieves a trustless swap, even between chains that use different technology and different architecture, potentially. That's a cool thing to talk about, but I think I haven't left myself enough time, especially considering our long lunch, to really discuss why the hash time lock contract works. So I will say, if you'd like to see a really cool invention, look up the hash time lock contract. There are many good explanations of it. If people want to talk to me about it afterwards or tomorrow, I'm happy to discuss why it works. But this is an example of it. And again, we can look at the code really quickly. Yeah. So this one has, again, two different branches that call two different functions, right? The left branch calls complete spend, and the right branch calls cancel spend, which are both functions that we define in the contract. And the complete spend checks that the password is correct. The cancel spend doesn't require the password, but does require a timeout. It requires it to be a certain time in the future. If it's not that far in the future, this branch is not available yet. Okay, I have a document on time locks. I'm not going to discuss the technical content of this document. I just want you to see that it's there on the Simplicity documentation website. So if you want to learn about how to enforce time locks in a Simplicity contract, hopefully this is all of the information that you will need. There are many examples. There's example code. There are charts about how to use each form of time lock. I am again happy to talk about this if anyone has more specific questions, but I hope that this document will be useful to you. Okay, I think I just have two more things in the code space, and then I think that's the end of the demos. So I actually demonstrated this before, but if you want to see the Python bindings in LWK, you can use this as one example to see how the Python bindings in LWK work. Right, so we have again the pay to public key contract, but instead of using HAL simplicity on the command line, we have a Python script that builds the transaction and builds the witness and submits the transaction and witness and spends the pay to public key contract. So if you're interested in doing development of applications that interact with SimplicityHL in Python, this would be a good example to look at. Again, this is considered to be in alpha, so if you do find any problems, please let us know and we can try to get them addressed, but we may not be able to get them addressed during the hackathon. But if you run these commands, doesn't necessarily have to be inside the code space, but you can run these commands inside the code space or otherwise. Run this Python program, it will build the transaction, it will spend the transaction. I did demonstrate that briefly before. So the worst thing for me about code spaces on GitHub is when you're in the shell and you want to delete a word using Control W, that's also close tab in the web browser. So this is about the 30th time that I have tried to delete a word in my terminal with Control W and closed my code space tab. Okay. It wasn't cargo, I want to run simplex. Okay, so one thing that I mentioned before is if you run simplex build, if you've referenced a specific the file extension that we use for SimplicityHL is SIMF, S-I-M-F. This refers to an older name of the SimplicityHL language before it was called SimplicityHL. If you have a specific SimplicityHL contract referenced in your simplex.toml, then Simplex build is able to generate Rust code to interact with that specific form of contract, right? And I think I showed that before. We can open that here. It's going to be in examples, basic, source, artifacts, right? This is the code that was auto-generated from Simplex build. So now it's up here. And this is some Rust code that is able to interact with the contract. Again, specialized to that particular contract. And in the code space, I should be able to, if I don't say Control W, also run simplex test. Now, if you run this yourself in the code space and you haven't run it before, you are going to compile 242 Rust programs. And if you're running it in your browser, you're going to compile 242 Rust programs on a relatively slow and underpowered VM provided to you by GitHub. So it might take you about 15 minutes. So I think it's good that I ran this before because it's only compiling about 5 of them, which might finish in about a minute. But if you're running this on your own machine, it will probably be pretty fast. But the browser code space, GitHub gives you not a very fast machine. I think they're giving it to you for free, so that's nice. But it's not very fast. Okay, we're at 238 out of 242. Right. And again, what I'm demonstrating here is simplex test, which is actually a very powerful tool in various ways. It really sets up an entire complete test environment, which includes an entire local elements D. So you're essentially running your own Liquid network on your own machine without even having to configure it at all. Now Pablo has another workshop that he's given about how to configure elements D for a test network on your machine. And it's about an hour workshop. It's a really good thing to do if you're doing elements or Liquid development, to have your own network where you can control everything. But it takes about an hour to learn to set that up. And simplex test does it for you automatically. So that's really quite convenient and quite powerful. And again, your tests then are not going on the public Liquid testnet, which you may also prefer for privacy. They're also faster, right? You also can't run into API rate limits because it's all just on your own machine. Okay, we're at 240 out of 242. Again, I'm sorry for the slowness. We're just running this on the free VM from GitHub. This would have, if I hadn't run it before at all, it would have taken 15 minutes or something. But basically what this is going to do in a relatively automated fashion is create a local test environment and then actually run a complete test transaction inside that local environment with this specific contract. And you can also, okay, running one test. Here we go. Right? Okay. So it's possible to see a lot more detail about what happened, but again, just running this one simple command, we got a lot of great stuff because it ran a local elements D, it ran a local, essentially, Liquid-like test network all on that machine in the code space. And it actually completed the transaction with it successfully using this contract. So you can set up a whole series of tests. It's a nice testing environment. We do have some colleagues who are using Simplicity for some real stuff, who are developing in Rust, and they're quite excited with this because they're saying, wow, I didn't know how to do tests, or they were slow, or they would sometimes time out, or they would sometimes fail. Now I can just put them all in one place in my project, and they run locally, and they're realistic, and they complete. So it's a cool testing environment. So if you're planning to develop in Rust, this really is a very helpful tool for a lot of the surrounding context for that. Let me just close by pointing out, I think that's everything from the code space, right? Just going to close by pointing out one page on our docs website. So I also just wanted to point you at this if you want to see some things that people have been doing with Simplicity already. At some of the user interfaces that they've created, some of the tools that they've created, right? We have this Simplicity DEX. This is an options trading mechanism. We have a lending protocol, which I've alluded to a couple of times, and I showed you a mock-up of the mobile user interface. Actually have a post-quantum signature verifier. In addition, there's a Stark, which is a kind of non-interactive zero-knowledge proof. There's a Stark verifier in Simplicity. There's Swaption, which is a binary options system. This is a demo of Astrolabe, which is not publicly available to interact with, but you can see a video demo of what it's about. That's an insurance investment product using Simplicity. And DeadCat, I alluded to, is the prediction market that's been implemented using Simplicity. It's not publicly hosted to trade on, but you can see all of the source code and see how a prediction market might be implemented. So these are some really quite extensive projects, which are quite fun and impressive. And sorry, there's also Anchor from OceanSlim, which is an automated market maker. Interesting curiosity about this, OceanSlim also, so Resolver is a company and Sideswap and Starkware are companies. OceanSlim is a person. He has created this automated market maker. He also wrote his own high-level language for Simplicity instead of SimplicityHL. So Anchor is actually not written in SimplicityHL. So if you look at that source code, you may be very confused because it doesn't look anything like the source code that I showed you here, because it's actually written in a different high-level language, and OceanSlim wrote a transpiler to transpile that into SimplicityHL. And it then gets compiled into low-level Simplicity from there. Having said that, it's a really cool project, right? And then I mentioned that we have the examples, right? And we're envisioning that it will be used for quite a variety of other things. And really looking forward to seeing more ideas and more implementations, more uses of these tools, right? Oh, yeah. These are actually about the things that I just demonstrated for you. I'm sorry that I neglected to actually show the... That would have been great to show you the slides about all of these things while I was demonstrating them. I just entirely forgot that I had slides talking about each of them. Okay, this is my last slide. So we did create a hackathon registration site on DevPost at simplicity-turin.devpost.com. I did send that out on Telegram. So tomorrow, we have this space again all day for those who want to participate in the hackathon. We have a $3,000 prize in Bitcoin for the first place, and we have our Jade hardware wallets for second and third places. As I said, I don't think we'll be able to do judging tomorrow, so we'll have to contact people afterwards. But we will contact teams afterwards and announce winners afterwards. So if you're interested in that, please do sign up on DevPost. And please do come back tomorrow. I'll also be here to answer questions and try to receive feedback, offer help in the hackathon. I think it'll be fun. Sometimes these events do turn up new bugs and new, documentation issues, toolchain issues. So perhaps we'll find some interesting bugs that we can report back upstream that we can get fixed. But again, I really appreciate everyone's presence, participation, patience. I know, again, that we threw quite a lot of information at you in a relatively short time. It's been great to be here and great to have you here. And I want to thank you all very much for your interest in our technology. I'll be around for a bit, so I'm happy to have more discussions, take more questions offline here. And I am going to send on Telegram all of the links. So for those of you who didn't scan the QR codes, I'll send a message on Telegram with all of those links. And again, tomorrow I'll also have a new Explora key to avoid rate limiting if you want to make anything that queries the Explora API. Thanks. I think that's it. Okay. I'll just hang out up here, and if anyone has any immediate questions, feel free to come up and chat.